It's almost that time. Are you ready?
I don't think you're ready for this.
This is what we've been waiting for! It will set us free. Shut up!
And here we go.
Welcome to React GG, the interactive way to master modern React. When we started making this course, our goal was ambitious: make it the best programming course ever created. Over a year and a half later, we couldn't be happier with how it turned out. Now, before we dive in, here are some things to help you get the most out of the course. First, despite the dopamine rush you just got when you gave us money, you haven't actually accomplished anything yet. Don't let this course collect dust with all of those other Udemy courses you've purchased over the years. Second, learning new things is hard.
Learning is fun, now the dance has begun. Fall in love with learning. Lean back, then we hit the road.
We've tried our best to make this course as simple and as enjoyable as possible, but at the end of the day, you're going to have to sit down and put in the work. It'll be hard, but if you do, and you're able to get through the course, I promise you'll know more React than most senior React developers. Third is how we think about education. A lot of Twitter heads will preach complexity and sell you their course as the cure. That's not really our thing. We are more interested in helping you establish a first principles mental model for how to think in React than we are teaching you how to glue a bunch of NPM packages together. You can see that in how we've structured the course. Each time you're introduced to a new topic, you're given some text and a video about that topic. From there, once you've gone through both, and we recommend you start with the text first and then watch the video as a review, you're given a quiz as a gentle test of your understanding. If you find the quiz to be too difficult, go back through the text and video one more time. The reason for that is this entire course is linear, meaning each section builds on top of the next. If you move on before feeling comfortable, it'll probably just get worse. Finally, the most important part. Before you move on to the next section, you'll be given a collection of challenges optimized for scenarios you'll see in the real world. If you're able to get through all of these, you can feel confident that you're in a position where you can move on to the next topic. And if at any point you get stuck and aren't sure what to do next, create a new thread and we'll be there to help. This course wasn't cheap, and the opportunity cost of your time going through it is even more expensive. We don't take that for granted, and we hope it lives up to the bar we've set for ourselves. Good luck.
Follow learning. Follow learning.
Believe it or not, when React first launched, it was not well received. Developers really didn't like it, and at first glance, why would they? It was drastically different than anything that had come before it. So the question is, how in the world did React go from sentiments like this to being universally loved and mostly respected? To answer that, we need to go back to before React was created. At the time, building for the web was different. jQuery, Backbone, and Angular dominated discussion. jQuery was the most popular way to build for the web. It embraced websites for what they truly were, a tree of DOM nodes. With jQuery, the state of your application lived inside the DOM. Whenever you wanted to update that state, you'd imperatively traverse the DOM, find the node you wanted to update, and then update it. jQuery revolutionized building for the web by both creating a simple and unified abstraction over manipulating the DOM that worked in any browser, regardless of typical browser compatibility issues.
It's incredibly aggravating for me to have to deal with all these cross-browser issues all the time.
Sure.
So I was constantly just, I wanted to develop my app in Firefox to have it just work in Internet Explorer, and
Sure.
it just wasn't possible.
Right.
So there was existing frameworks. Like at the time, there was Prototype and MochiKit, and I think Dojo was starting to come around as well. But none of them, I felt that they didn't have the exact level of dedication towards fixing the bugs that I wanted, and they didn't have the API that I want. I wanted something that was nice and terse and short, that just could let me write and get done.
Ironically, jQuery's biggest blessing was also its biggest curse. Turns out relying on shared mutable state was a bad idea. With jQuery, what started out as a simple way to update DOM state typically devolved into a mess of spaghetti-like mutations that were both hard to predict and keep track of if you weren't careful.
Fine, you're doing splendidly. Speed it up!
What jQuery needed was something that encouraged a little bit more structure.
Now it's time for you to jump into more Backbone, you little devils.
Backbone.js invented the model view controller pattern. That's a joke. But it was the first popular JavaScript framework that embraced the traditional software design pattern and brought it to building for the web. In just 2,000 lines of code, Backbone allowed you to decouple your application state from the DOM. Instead of living in the DOM, Backbone state lived inside of its models. From there, whenever a model changed, all the views that cared about that model state would re-render. And that was it. Backbone's entire philosophy was to be as minimal and unopinionated as possible. So much so that the default implementation of Backbone's method responsible for rendering the view was a no-op. That's a fancy way of saying it was entirely up to you to implement your own view and templating strategy. But you know what wasn't minimal and unopinionated?
Anyway, so what is AngularJS? It's what a web browser would have been had it been designed for web applications.
This introduction talk was the perfect representation of the AngularJS project. Not because of what was said, but because Mishko did it entirely barefoot. A perfect analogy for the fact that AngularJS did whatever the fuck it wanted. The idea was simple. What if HTML was more powerful? With AngularJS, you got everything you'd ever want, and much more, out of the box. Two-way data binding, data filters, routing, controllers, dependency injection, templates, literally a mini version of jQuery. AngularJS changed the game because it was a true, opinionated, all-in-one framework for building web applications. Now, you need to remember the environment we were in here too. This was 2011. Being a pure front-end developer was much more uncommon than it is today. The highly opinionated nature of AngularJS was convenient for back-end developers who were given the unfortunate task of working on the front end. This wasn't as uncommon as you might expect, and it fueled AngularJS's popularity. The problem, among other things, was that AngularJS loved two-way data binding.
80% of what you do is just DOM manipulation, DOM munging. And 20% of what you're going to do is the actual interesting stuff of what the application does, right? And so we want to get rid of this 80% portion. So how do we do that? Well, as I said, Angular is kind of like a spreadsheet. So if I start typing, notice same exact behavior, it updates immediately, but notice how simple it is.
Two-way data binding was Angular's way of updating the view whenever the model changed, and updating the model whenever the view changed. In theory, this was nice because you didn't have to worry about doing manual DOM manipulation yourself. In practice, well, implicit state changes usually lead to code that is hard to follow and hard to debug. It also led to performance issues since AngularJS had to constantly scan your app looking for state changes. Now, though they were the most popular, building for the web consisted of more than just jQuery, Backbone, and Angular. But regardless, the majority of these post-jQuery frameworks had one thing in common: models. And specifically, models that we kept in sync with the view. But what if you could avoid that problem entirely?
The simplest way conceptually that we've found to build views, to build this piece, is to just basically avoid mutation altogether. What we found is that if you could just, anytime your data changes, blow away our view and just re-render the thing from scratch, like that would be so much easier. From a developer standpoint, we want to be able to say, okay, anytime anything changes, we're just going to start over. We're just going to blow everything away and re-render from scratch. But we want to do it in a way that's actually performant and actually provides a good user experience, right? So the solution that we came up with internally is called React. And here is a JavaScript library for building user interfaces.
One of the core innovations of React was that they made the view a function of your application state. All you have to do is worry about how the state in your application changes, and React can handle the rest.
And this is actually really simple because it's so declarative. Every place we display data is guaranteed to be up to date. And we do it without magical data binding, without dirty checking the model, which can be expensive. And of course, this is a modern framework. There's no more explicit DOM operations, and everything is declarative.
But this was really only half the picture. The real innovation happened when you encapsulated this idea into a proper component-based API. By doing so, the same intuition you have about creating and composing together functions can directly apply to creating and composing components. However, instead of composing functions together to get some value, you can compose components together to get some UI. To truly embrace a component-based API, React needed a way to allow you to describe what the UI for a component would look like from inside the component itself. Now, this is where most of the initial hate for React comes from, and it had to do with React's interpretation of the separation of concerns principle. If you're not familiar, separation of concerns is a software design principle for separating a computer program into distinct sections. Historically, the way you adhered to this on the web was to have your HTML separate from your CSS, which was then separate from your JavaScript. But React had a different interpretation. In React's opinion, anything that had to do with rendering the view, whether that be state, UI, and in some cases, even styling, was part of its concern. To accomplish this, React needed a way to allow you to describe what the UI for a component would look like from inside that component itself. Well, describing UI is already a solved problem. That's what HTML is really good at. But you can't mix HTML and JavaScript, right?
If you pay attention to the API, React is a JavaScript first paradigm. And there's a lot of reasons for that. Because JavaScript is powerful, it's flexible, it's a language you already know. You're able to represent interactions and logic that are just really hard to do in other more constrained languages like templating syntaxes. A lot of other frameworks are kind of letting you define your entire UI in JavaScript alone. But there's one thing about JavaScript that ends up kind of like getting in the way as you build deeply nested components. As you start paying attention to these braces here, you don't even know which one corresponds to the other one. And so what we did at Facebook is we addressed this problem by inventing a new syntax that's still every bit JavaScript, but it's a little more familiar to somebody that has experience with templates or HTML.
What made JSX different was it combined the power and expressiveness of JavaScript with the readability and accessibility of HTML. If you were already comfortable with both JavaScript and HTML, which you probably were if you were building web apps, then you could get up to speed with JSX in a matter of minutes. Yes, it was weird and different, and most people hated it at first.
I hate it, but I love it.
But once you used it in an actual app, it became clear that React was onto something with their interpretation of the separation of concerns principle. Not only that, but by embracing both JSX and React's component-based API, all of a sudden what used to require imperative operational-like code could be abstracted behind a declarative API. This not only enabled a better developer experience, but also a vibrant ecosystem of third-party components. You've probably heard these terms before.
It's declarative.
Declarative.
One's imperative, one's declarative. Super declarative. It's declarative.
Declarative transitions.
Declarative way, imperative way, declarative way, imperative way. Declarative way to imperative way. Yeah, whenever we have a declarative API, we've got an imperative one.
What exactly do these terms mean? The problem is if you look them up, you usually get something like this, where imperative programming is how you do something, and declarative programming is what you do. The problem is that makes perfect sense after you've learned about the difference between imperative and declarative programming. Combine that with the fact that people use the word declarative to mean something is good nowadays, and the topic is fairly confusing. But let's back up, because there is something in these definitions. To better make sense of them, let's look at a real-life example. Say we've been listening to a lot of Beyonce lately and had a craving for a certain American casual dining restaurant chain.
Come on into Red Lobster.
One approach for getting a table may look like this, where we walk up to the waiter and say, I see that table over there by the Gone Fishing sign is empty. My husband and I are going to walk over to the bar, take a ride to the bathroom, walk past the 2 tables, and then sit down. Another may simply look like this. You walk up to the waiter and say, table for 2, please. One of these approaches, the imperative approach, is focused on how you're going to get a table. The other, the declarative approach, is focused on what you want, a table for 2. Let's look at some code. Say we wanted to write a function called double, which takes in an array of numbers and returns a new array after doubling every item in the original array. One approach may look like this, where we times each number in the original array being passed in by 2, push that into the new array, and then return the results. Next, what if we wanted to write a function called add, which takes in an array and returns the results of adding up every item in that array? Again, a similar approach may look like this, where we create a variable and set it equal to 0, then we add the value of each item in that original array that's being passed in to this variable and return it. Last, let's say we wanted to add a click handler to the element which has an ID of button. When clicked, toggle the highlight class as well as change the text to add highlight or remove highlight. One approach may look like this, where first we'd get the element that has an ID of button. From there, whenever the user clicked the element, we toggle the class and, based on its current state, update its text. Now, is this code bad? Well, of course not. But in each of these examples, we're conforming to the operational model of the machine by describing how we want to accomplish a certain task rather than what we want. Another way to think about the difference between imperative and declarative code is if you can trace the execution of the program as it runs. In each of these examples, we can very clearly trace how the program is going to run. This forces us to, again, think like a computer in a very operational way rather than as a human. So now the question is, how can we update this code to be more declarative? Let's take a look. For double, we can leverage JavaScript's map method to return a new array after multiplying every item in the original array by 2. For add, we can leverage JavaScript's reduce method to return a new number after adding each item in the original array to that number. And for our button logic, we can encapsulate that behind a button component. The library we use for this is just an implementation detail. The bigger takeaway is that writing reliable software is all about properly managing complexity. What we've done is we've taken our imperative operational-like code and abstracted it behind a declarative API. In fact, many, if not all declarative APIs, have some sort of underlying imperative implementation. This makes sense. If our argument is that declarative code conforms to the mental model of the developer rather than the operational model of the machine, And ideally, we'd want to abstract away most imperative code behind a declarative API. Now, if it still hasn't clicked, let's look at some purely declarative code. Here's some SQL which is selecting all of our Mexican users. It's the perfect representation of declarative code. We're describing exactly what we want, Mexican users, without having to instruct the computer how to do it. Another example of declarative code is HTML. We're not concerned with how the web browser is parsing our article element and displaying it to the screen. Instead, we describe what we want, a new header and a paragraph, rather than how we want it. Another example, CSS. Again, what, not how. Now, another less spoken of benefit to declarative code is that your program can be context independent. This means that because your code is concerned with what the ultimate goal is, rather than the steps it takes to accomplish that goal, the same code can be used in different programs and work just fine. This is hard to do with imperative code because often, by definition, imperative code relies on the context and current state of the program it's running in. Table for two, please, is universal, where I see that table over there by the Gone Fishing sign is empty, works only at the highest quality establishments. It may seem basic, but as a software developer, your primary job is to maximize the predictability of your program. Think about it. The root cause of any bug you've ever experienced was because the expectations of the developer diverged from the reality of the program. Assuming this is true, it's not unreasonable to think that we should spend at least some time thinking of how we can make our programs more predictable. Now, to better figure this out, I think it would be beneficial to narrow our scope just a little bit.
So alone.
Make our apps more predictable is too broad of a goal to be of any practical use. Instead, I think it's safe to assume that we can make our apps more predictable by making the individual pieces that make up our app more predictable. And what are those pieces? Usually, they're functions. A function is a process which takes some input, an argument, and calculates some output, a return value. Functions, by definition, are simple. The problem is nothing screws up the simplicity of a definition quite like the complexity of reality. In reality, functions are often the junk drawer of our applications. In the real world, we can solve these sort of eventually chaotic scenarios by having a strict set of rules and then diligently adhering to them. Are there a set of rules that we can make to keep our functions from becoming unpredictable over time? To better answer that, let me ask a different question. What makes a function unpredictable? If we can answer this question, then we can create a set of rules to avoid those scenarios. In my opinion, there are two big offenders: side effects and inconsistent outputs. Let's look at side effects first. Earlier, we defined a function as a process which takes some input, an argument, and calculates some output, a return value. Anytime a function does anything other than this, it's said to have a side effect. Take this simple function. It both relies on state other than the input it receives, and by mutating to-dos, it creates an observable change to the program, therefore it has a side effect. Now what about this one? It doesn't create an observable change to the program, but it does rely on state other than the input value it receives. And yes, state from an external API still counts. Therefore, this function has a side effect. Now what about this one? You probably get the idea by now. We're not relying on state other than the input value it receives, but we are creating an observable change to the program. Therefore,
it's just a side effect, they say.
So why are side effects bad? Well, they're not necessarily bad, they're just unpredictable. One problem is because they depend on the context outside of their local environment.
I'm lost! Where's the line? It just went away. Dude, what do I do? Help!
They're contextual to the current state of the application. If the state of the application changes, they'll behave differently. Take this function, for example. This function will only work in a program where tax rate is both a variable and that variable is a decimal. If tax rate gets mutated, or worse, deleted, calculate final price will behave differently.
Unpredictable.
And with that, we have our first rule: avoid side effects. The next culprit in making functions unpredictable are inconsistent outputs. If a function doesn't have a return value, it's unpredictable. In this scenario, you can assume the function is either doing nothing, which is unlikely, or it has a side effect, which breaks rule number one. Similarly, if a function, given the same input, doesn't consistently return the same output, it's also unpredictable. There are a variety of built-in methods you probably use regularly that are unpredictable for this exact reason. And it's not just built-in methods that have this problem. Take this function, for example. We already know it's unpredictable because it breaks rule number one, but beyond that, it's even more unpredictable because, given the same input, it will return inconsistent outputs. Even if everything goes right, the promise we get back from get GitHub profile is different for each invocation. And worse, if something does go wrong, there are a variety of other things that aren't the user's profile that might get returned. So now we have our second rule: Keep your outputs consistent. So what exactly are the benefits of following our two rules? Well, it's obvious that writing functions that follow our rules will make them more predictable and therefore less susceptible to bugs. However, in doing so, there are also some other non-obvious benefits. Because these functions don't depend on the context of the application and instead receive their inputs via explicit arguments, they're entirely program agnostic and therefore extremely composable and reusable. Next, because these functions always return the same output given a certain input, the results can be cached. Say we had an expensive isPrime function that calculated if a given number n was a prime. This function is entirely predictable. It doesn't contain any side effects, and given the same input, it'll always return the same output. In this scenario, it doesn't make sense to invoke isPrime more than once for a given number. Invoking isPrime passing in 997 is always going to return true no matter how many times we run it. Because it's predictable, we can cache the result. With this change, one thing you may have noticed is that isPrime is now technically an impure function since it depends on the context of the application, specifically prime cache. This is a good example of how, in the real world, you can't always write pure functions. With that said, notice that we've encapsulated isPrime and prime cache into their own module. The only way to modify prime cache is via isPrime, and no other function in our application has access to or depends on prime cache. Even though isPrime is technically impure, it's about the purest impure function we can write, and I'd still consider it pragmatically predictable. Next, because these functions are free of side effects and don't depend on the context of the application, they're optimized for testing. You can simply test that, given a certain input, the output is consistent with what you'd expect. Now, if it's not already obvious, this idea isn't a new concept that we've invented. Instead, we've essentially recreated the functional programming principle of pure functions. A function is considered pure if it contains no side effects and if, given the same input, always returns the same output. By embracing and striving to keep your functions pure, you'll naturally increase the predictability of your program while minimizing the amount of bugs it has. So, what does this have to do with React? Let's find out.
Do not panic! Do not panic! We are trained professionals! Now stay calm. We are going around the leaf.
One thing I love about React is that it feels like it's the answer to the question, what would HTML look like if it were invented today? The primary benefit of HTML is that it allows us to create rich, structured markup in a declarative way. In contrast, the primary benefit of JavaScript is that it gives us a set of tools for managing the complexity of building an application. React, of course, is a love child of the two, giving you the declarativeness of HTML with the feature set of JavaScript. But what does this actually look like? Let's say we had some HTML. Now, say we wanted to reuse this HTML on multiple pages. How would we go about doing that? The most common way is with something like this, the old copy pasta. It works, but it's not ideal. In JavaScript, this is already a solved problem. We can put this code in a function, then put that function in a module, then import that function anywhere we want to use it. Believe it or not, this is essentially React. I wasn't joking when I said React is the love child of HTML and JavaScript. If you've never seen a React component before, there's a good chance you're mildly horrified right now.
Monsters.
The first thing you'll notice is that a React component is just a function. Again, React loves JavaScript. The same mental model you have about functions could be directly applied to React components because, in the literal sense, they're just functions. The only change we need to make it a true React component is to capitalize the first letter of the function. The reason you need to do this is so that React knows it's a React component and not just a normal DOM element. And now, because we've encapsulated this function inside of its own module, if we export it, then anywhere in our application where we want to use it, we can just import it. Now, one thing to notice is that we're not going to invoke authors as if it's a normal function. Instead, we treat it as if it's an HTML element wrapping in angle brackets. Now, there's a lot happening under the hood between when JavaScript reads the component and when the browser paints the UI to the screen. But know that the final output is probably what you'd expect, where React replaces the component with the description of the UI the component returns. This is true regardless of how many components there are or how deeply nested they are. And since components are just functions, again, the same intuition you have about organizing functions and when to abstract logic to its own function can be directly applied to components. If you don't yet have that intuition, following the single responsibility principle is a decent barometer for when and where to create components. When you follow the single responsibility principle, you're likely to end up with a lot of smaller components. Just like with functions, this isn't a bad thing. However, it can overwhelm your component directory if you're not careful. Take this code, for example. It follows the single responsibility principle, but since we're creating a new file for each component, it's a bit messy. Instead, here's a good rule of thumb you can follow. If you have a component that's being reused somewhere else, put it in its own file. If not, just create it inside of whatever file you need it. And now before you go, there's one last thing we have to do, and it's answer a question from the previous video. What do pure functions have to do with React? Well, as a rule, any component you create needs to be a pure function. We'll learn all about strategies for doing this later in the course. Whenever you have a system that is reliant upon composition, it's critical that each piece of that system has an interface for accepting data from outside of itself. Without the ability to pass data, in this case username, to each of our functions, our composition would break down. Similarly, because React relies heavily on composition, there needs to exist a way to pass data into components. This brings us to props. Props are to components what arguments are to functions. In fact, the same intuition you have about arguments and functions can be directly applied to components and props. Naturally, there are two parts to understanding how props work: how to pass data into components and accessing the data once it's been passed in. Passing data into components should feel pretty natural because you've been doing something similar ever since you learned HTML. You pass data to a React component the same way you'd set an attribute on an HTML element. Here, we're passing in a name prop to the hello component. It's important to note that we're not limited to passing just strings as props. Just like we can pass functions or any other value as arguments, so too can we pass any value as props. One thing you may have noticed is that sometimes we have to wrap what we're passing in inside of curly braces. Can you spot why that is? The rule is that anytime you're passing a prop that isn't a string, you must wrap it inside of a curly brace. The reason for that is curly brace allows you to use JavaScript inside of your markup. Following that rule, though this looks a little weird, you can even pass object literals to components as props. Notice we're using two sets of curly braces. If you think about it, that makes sense. We have an object which we want to pass as a prop, and since it's not a string, we wrap it in another set of curly braces, getting us two pairs. Now before we look at how to access props, there's one more thing to be aware of with passing them. If you pass a prop without a value, that value will be set to true, meaning these are equivalent. So now the big question, how do you access props from inside the component? Well, since components are just functions, it's pretty simple. React will put all of the props on an object and pass that object as the first argument to the function when it renders. Regardless of how many props you pass to a component, each prop is added as a key on the props object. And because props is just an object, you can also destructure it if you'd like. Now take a look at this anchor element. Is there any data we're passing it that's not as an attribute? What about the home text? As part of the API for almost every HTML element, you can pass data via the opening and closing tag of that element. Now, what if instead of those being regular HTML elements, they were React components? Instead of passing data into components via setting attributes as we usually would, we're passing data into the component via the opening and closing tags of the element. In this scenario, how would we then access the data from inside the component? React, again, makes this pretty simple. Whatever is between the opening and closing tag of an element will be accessible inside of the component as a children property on the props object. You can think of a component with a children prop as having a placeholder that can be filled by its parent component. Because of this, it's common to utilize children to create layout type components that encapsulate styling and logic, but leave the content to the consumer of the component. A common example of this is a modal component. Notice that we encapsulate the styling and logic of the modal into the modal component, but we can specify what the contents of modal are when we create the modal element.
An absolutely seamless use of props.
Here's a question for you. If this is called a function definition, this is called a function invocation. If this is called a component definition, what is this called? Here are some of the most common answers, all of which are incorrect. The primary reason for the confusion is because there's an important but subtle step between when React evaluates your code and the browser sees it. This makes sense. The browser can only understand JavaScript, and though JSX is a syntax extension to JavaScript, it's still not browser compatible JavaScript. The problem isn't anything new. We've been compiling non-browser compatible syntax like Elm, TypeScript, and CoffeeScript to JavaScript for years. So how exactly do we go from this to JavaScript the browser can understand? The answer lies in what React calls an element. A React element is an object representation of a DOM node. This definition gives us some interesting insight into how React works under the hood. An element isn't a DOM node. Instead, it's an object representation of it. This React element, being an object representation of a DOM node that looks like this. The way React works is it'll keep references to all of the elements in your application, and if one of those references changes, React will then know where exactly in the DOM it needs to update. In order to create a React element, you have a few options, one of them being React's JSX runtime package. This function takes in two arguments. The first is a tag name string, like div or span, and the second is an object of attributes you want the element to have. In our case, a class name of header with the text profile as its contents. What it returns is a React element. Notice there's no JSX here. It's all just JavaScript. What's interesting about learning React is that typically one of the first things you're taught are components, and that components are the building blocks of React. But as we can see, that's not true. Elements are the true building blocks of React. Components, by definition, are just functions that optionally accept input via props and return a React element. And you're not only limited to creating React elements from native HTML elements like span and div. You can also pass in other React components as the first argument to the JSX function as well. When the JSX function sees that there's a component as the first argument, it will recursively render that component as well as all of its children components in order to get all of the React elements and the final description of the UI. Remember the badge component from the props lesson? Here's what it looks like using the JSX runtime package. So now the big question you're probably wondering, what's the difference between writing JSX and using the JSX transform? As far as the browser is concerned, nothing. As you can imagine, creating a description of your UI with JSX function invocations isn't terribly ergonomic, which is why we have JSX. At build time, all of the JSX in your application gets compiled to JavaScript via JSX invocations that the browser can understand. So now that we have a little bit more context, let's go back to our original question. If this is called a function definition, this is called a function invocation. If this is called a component definition, what is this called? We call it creating an element, because after the JSX is compiled and the JSX function is invoked, that's what we get back, an element. In fact, all of these examples are showing different ways to create React elements, regardless of if we're using JSX or the JSX transform API. To build a modern interactive application, you're going to need the ability to listen to and respond to events, obviously. Thankfully, the API to do this in React is fairly simple, and it involves two things you're already familiar with, props and functions. Let's start off with the most basic example, alerting whenever a user clicks on a button. First, we'll start with a button element. Now let's create a function which will encapsulate the logic for what happens when a user clicks on the button. We'll call it handleClick. Finally, we want to tell React to invoke our handleClick function whenever a user clicks on our button element. To do that, we can pass button an onClick prop, which will be set to our handleClick function. Now, whenever the button is clicked, React will invoke handleClick. Basic, yes, but this example demonstrates some important concepts and patterns that are consistent regardless of the complexity of the event you're listening for. First, it's a good idea to encapsulate the event handler into its own function, and it's common practice to name the function handle plus the name of the event, in our case, handleClick. Next, you'll notice that we're passing our event handler as a reference to onClick, not as an invocation. Note the difference between these two onClick props. For the record, this is true for passing any function as a prop and not just event handlers. Always pass your functions as references, not invocations. Next, you'll notice that we created our event handler inside the component, not outside of it. This is also a common pattern, but it may feel unintuitive at first. Can you think of why we do this? To see why, let's adjust our example a bit. Instead of alerting, let's alert whatever is passed in as the message prop to our alert button component. By declaring our handleClick function inside of our component, we automatically have access to the message prop via JavaScript's normal lexical scoping rules. Notice what happens when we move handleClick outside of the component. We no longer have access to message via scope. Instead, we have to pass it as an argument to handleClick, which forces us to create another function that we pass to onClick. This indirection is unnecessary and is a good indication that we should move handleClick back inside of our component so we can take advantage of lexical scoping. One reason why your intuition might be telling you to move handleClick outside of the component is because you're worried about performance. If it's inside the component, then JavaScript will have to recreate the new function every time the component renders, right? That's correct, and that's mostly fine. Turns out, JavaScript is really good at creating and destroying functions, to the point where it's usually a non-issue. For the very few edge cases where this isn't true, we have some options we'll learn about later in the course. So at this point, you know how to add a click handler to a button, but let's look at a scenario that isn't straight out of a generic React tutorial. Say we wanted to build something like this, a little game where the user has a certain amount of time to copy the main emoji from a list of smaller emojis. Fun. Let's start off with the easy parts first, just the UI. We'll have an array of emojis, a function for selecting a random emoji, and some JSX. Now let's work on our event handler that will pass as an onCopy prop to each of our three emojis. This event handler will need to check if both the user copied the right emoji as well as if they did it in under 5 seconds. This does bring up a new scenario though. We now need to know some specific information about the event that was triggered. Specifically, we need to know which emoji was copied so we can see if it was the right one. This brings us to the last piece of knowledge you need for managing events in React. Whenever an event handler is called by React, React will pass an object as the first argument to the event handler that contains all of the information about the event that was triggered. In our example, that event object will look something like this. Though there's a lot of extraneous data here, there are a few things that'll be helpful to us, namely the target and timestamp properties. Target is the element that triggered the event. We can use it to figure out which emoji was copied by comparing its inner text to the selected emoji. timestamp tells us how long it's been since the document finished loading and the event occurred. We can use that to figure out if the user copied the emoji before 5,000 milliseconds had passed. And if neither of those cases evaluate to true, they're a winner. Now the only thing left to do is create our event handler for our reset button. This one is simple. We'll just call location.reload to reload the page. And that's it. Now if the user copies the right emojis in under 5 seconds, they'll get a winner alert. Now before we end, if you're an experienced web developer, you're probably aware that there are a lot more events you'll eventually want to listen for other than just onClick and onCopy. For your future reference, here's every event you can listen for inside of React. React, in its purest form, is a library for building user interfaces. It's so simple that the entire mental model can be represented as a formula. If we break it down, we've seen how you create your view with JSX and how you encapsulate that view inside of a function to get your component. But there's still one piece of the formula we haven't talked about: state, and specifically, the ability for individual components to own and manage their own state. This is what makes React so powerful, and it's what allows you to build complex user interfaces out of simple, isolated components. So what does adding state to a component look like? Let's say we were building a simple counter app that keeps track of how many times a user has clicked a button. Your first assumption might be to do something like this. After all, React is just JavaScript, right? And the way you add state to a function is by creating a variable. Unfortunately, this won't work. Can you spot why? Ironically, it won't work for the same reason, because React is just JavaScript, and that's not how JavaScript works. This is clear if we take React out of the picture entirely. Here's a normal JavaScript function. Without React, you wouldn't expect the count variable to persist across different function invocations. Each invocation is its own isolated environment with its own scope and context. With React, it's no different. So how do we get around this? Well, we need some help from React. Specifically, we need a way to tell React to preserve the value of count between different invocations of our counter function. React refers to these function component invocations as renders. Lucky for us, React comes with a hook that does exactly this, called useState. Now before we get into useState, what in the world is a hook? You can think of hooks as special functions that allow you to get help from React. The reason they're special is because they have a few limitations. Namely, that they must start with use, and you can't call hooks inside conditions, loops, or other nested functions. We'll go much deeper into hooks throughout the course, but here's a simple mental model you can use for them. Hooks are just functions, but it's helpful to think of them as unconditional declarations about your component's needs. You use React features at the top of your component, similar to how you import modules at the top of your file. Okay, let's go back to useState now. UseState is the blessed way to preserve a value across component renders. It comes built in with React and can be accessed via react.useState. It takes in a single argument, the initial value for the piece of state, and returns an array with the first item being the state value and the second item being a way to update that state. You may notice that this code feels a little clunky. This stems from the fact that useState returns an array. We can clean this up by using array destructuring. If you're not familiar, array destructuring allows you to pluck multiple items from an array and assign them to variables in bulk. So now that we know the purpose of useState as well as how it works, we can update our counter example from earlier to use it. Now, regardless of how many times React renders our component, the value of count will persist across all of those different renders. But this does bring up an interesting question. When does React render our component exactly? We have a whole lesson dedicated to this question later in the course, but here's a sneak preview. The answer is surprisingly simple. React re-renders a component whenever its state changes. Previously, you learned that useState is a hook that allows you to persist a value across renders and trigger a re-render when the value changes. You also learned how to use it, specifically that useState returns an array with two values, the first being the current value of the state, and the second being a function that can be used to update the state. Though creating a simple counter app gives us a gentle introduction to useState, it's not super practical. Let's look at some other use cases that'll give us more insight into how we can leverage useState in more scenarios. We'll have an app that walks through the following state progression. We'll start with a single piece of state. We'll add multiple pieces of state to the component. We'll update our state to see how we can manage that state when it's an object. And then we'll update our state to see how we can manage state when it's an array of objects. Naturally, though it seems stereotypical, the best app to build to see this progression in isolation is a to-do app. Don't let the simple nature of this app fool you. After this lesson, you'll have a first principles understanding for managing state in React, and you'll be able to apply it to any app you build, regardless of the complexity. In fact, if you felt that this course has been too simple so far, this is the lesson where it starts to ramp up. First, let's start with the UI for a single to-do item. Eventually, we'll create these dynamically whenever a user adds a new to-do item to their list, but for now, we'll hard code it. Next, we need to make our app interactive. Specifically, we want to give the user the ability to toggle the status of the to-do item. To do that, we'll add some state to the component to keep track of the status of the to-do item, add an event handler to update that state, and then hook the event handler up to our input via its onChange prop. At this point, whenever the user clicks on the checkbox, completed will be set to the opposite of whatever it was, and the component will re-render with the new value. Cool, and mostly worthless so far. Let's add some more functionality. Specifically, let's add the ability for the user to edit our single to-do item. First, to make our to-do item editable, we need to move it out of our JSX and into a state variable so it will persist across renders. Next, we'll need some state to keep track of whether the user is currently editing the to-do item or not. And then we'll add a method that toggles that new editing state and hook that method up to a button the user can click. Now, because we have our editing state, we can dynamically show or hide our input field based on that state. So at this point, whenever the user clicks on our edit button, the to-do item will be replaced with an input element. Now we need to make sure that whenever the user updates the input field, we also update the label on our state. To do that, we'll create a new handle update label method and pass that as an onChange prop to our input field. Now, whenever the user edits the value in the input field, we'll update our label state. So at this point, our app is progressing nicely, but you may notice something a little strange. Currently, we have multiple pieces of state representing one to-do item. That works, but it won't scale well when we add more to-do items. How can we fix this? What if we represented our to-do item as an object instead of individual state values? Now, we need to make two changes to our code to match our new state structure. First, we'll update our JSX to reference label and completed as properties on our to-do state rather than as individual variables. And then we'll update our event handlers to handle our to-do state as an object rather than as individual pieces of state. This brings up something interesting. Notice that we're passing setToDo a new object, but we're copying all the properties from the current to-do onto it using the object spread syntax. It's important to note that when you pass a value to useState's updater function, whatever the value you pass will always replace the current piece of state. What this means is that if you have a piece of state that is an object, it won't be merged with the current state. Instead of replacing the object, you most likely want to merge the new value with the existing state object. To do that, as you saw, we can use JavaScript spread operator to spread all of the existing key value pairs onto a new object, then pass that new object to the updater function. So at this point, our app is coming along, but unfortunately, it still doesn't resemble much of a to-do list. This highlights a problem with how we've currently architected our app. Right now, the state of each to-do item is coupled to our to-do component. On the surface, this seems like a good idea. We're keeping the state of each to-do item close to the component that renders it. The problem is it's a little too rigid. With this architecture, how would you go about adding another to-do item? Your intuition might be to just render another to-do element. But now we have multiple to-do items with the same label and ID. And not only that, what happens when we want the user to be able to create their own to-do items? How do we make it so our to-do composer element can dynamically create new to-do elements? What if instead of having each to-do component manage its own state, we lift that state up to a parent to-do list component? This would solve all of our problems. To-do list would own and manage the state of each to-do item, and then we can pass the data down to the components that need it via props. In fact, learning when and how to lift state up is one of the most important aspects of state management in React. Here's the rule of thumb. Whenever you have state that multiple components depend on, you'll want to lift that state up to the nearest parent component and then pass it down via props. Oftentimes when lifting state up, you decouple where the state lives from the event handler that updates that state. To solve this, you'll create an updater function in the parent component where the state lives and, via props, invoke that function from the child component where the event handlers live. All right, so back to our code now. Let's lift our to-do state up to a new to-do list component as shown here, and then pass it down via a prop to the to-do component. And now, before we update our to-do component, we need a way from inside of that to-do component to update the state that's now located in the parent to-do list component. Whenever you're in a situation like this, what you'll want to do is create a function in the component where the state is located, and then pass that function down via props. Then you can pass data back up to the parent component by passing an argument to the function that was passed down. So now back inside of our to-do component, we need to move some things around. First, we'll remove the local to-do state and accept it as a prop since it now lives inside of the parent to-do list component. Now, since we'll be rendering multiple to-do elements, we'll update the HTML4 and the inputs ID to be unique based on the to-dos ID. Next, we'll update our event handlers to use our new handle update to-do prop that we also passed down from the parent to-do list component. The biggest thing to notice is the relationship between handle update to do in the parent component and handle checkbox click and handle edit to do in the child component. I'll reiterate because it's perhaps the most important aspect of this lesson. Whenever the state you're updating lives in a different location from the event handlers that update that state, you'll create an updater function in the component where the state lives, and you'll invoke that function from the component where the event handlers live. In our case, the state of our app lives inside of our parent to-do list component. Therefore, anytime we want to update that state, we need to do so where it lives, in to-do list. Now notice that handle update to do has an updated to do parameter. This is how we get data from where the event handler lives in a child component back up to where the state lives in the parent component. It doesn't matter where handle update to do is called, it just matters that when it's called, it receives this updated to do argument. So at this point, our app is in better shape than it was before, but it's still not a to-do list. Let's fix that. In JavaScript, the way you create a list of items is by using an array. We'll do the same thing here by updating the state in our to-do list component to be an array of to-do objects rather than just a single to-do object. Now, if you try to edit a to-do item, you'll notice that we get an error. That's because we need to update our handle update to do function to treat to-dos as an array rather than a single to-do object. Now, before we do that, let's take a moment to learn about how you can update array state in React. Admittedly, the knowledge you need for updating array state in React doesn't have anything to do with React. It's all just JavaScript. This is a good thing because it means the knowledge is portable to other JavaScript projects, not just React-specific ones. You can break the process of updating arrays down into 3 use cases: adding elements, removing elements, and updating elements. Here's the canonical way to do each. To add an element to an array, use JavaScript's spread operator to spread all of the existing elements onto a new array with the new element. To remove an element from an array, use JavaScript's filter method to create a new array, filtering out the element that should be removed. And to update an element, use JavaScript's map method to create a new array, updating the specific element where appropriate. The takeaway from all of these examples is we're never modifying the original state array, and we're using built-in JavaScript array methods to make our transformations. Regardless of what type of change you're making, these things should always hold true. Now with this knowledge, we can now update our handle update to do function to treat to-dos as an array. We'll use map to create a new array, updating the specific to-do item that was passed to handle update to do. Now one thing to notice is that we didn't have to change the implementation of to do. All to do cares about is it receives a handle update to do prop that it can invoke, passing it the updated to do item. What happens when it's invoked is an implementation detail of to do list and is irrelevant to do. At this point, things are progressing nicely. Before we worry about adding new to-dos, let's give the user the ability to delete them. Again, the rule of thumb is we want to update the state where it lives. In this case, because to-do list is the component that owns our to-do state, we'll want to create our function for deleting to-do items in the same component. Let's call it handle delete to-do and have it take in the ID of the to-do item to delete as its only argument. From there, we'll pass handle delete to-do down as a prop to our to-do component. And finally, we'll add our new handle delete to do prop to an event handler inside of to do, and then invoke that event handler whenever the user clicks on our new delete button. So at this point, we have the world's most useless to do app. Though peaceful, without the ability to add new to-dos, it's not very useful. Let's start with changes to our to-do list component. One more time for those in the back. Because to-do list is the component that owns our to-do state, we'll want to create our function for adding to-do items in the same component. Let's call it handle add to-do and have it take in a new to-do item, which it'll add to our to-do state. Now we need to figure out where to invoke handle add to-do. We could invoke it in our to-do list, but that would require us to add a new input field and state to our to-do list component. Instead, let's abstract that into another component. We'll call it to-do composer, and it'll receive our handle add to-do function as a prop. Now inside of to-do composer, all we need to do is get the new to-do item from the user and then pass that to props.handleAddToDo. Now let's add some state and an input field to our component to keep track of the label of the new to-do item. Next, let's create a function that will handle actually creating our new to-do object. This function would usually live on a server somewhere so that we could generate unique IDs, but for our use case, we'll just fake it. And then from there, we'll create an event handler that will invoke our new handle add to do prop, passing it our newly created to do item, and then clear the state of the input field. Finally, we need to hook our handle add to do click event handler up to a new button the user can click to add their new to do item. And that's it. We now have a fully functioning to do app. Though it may have been painstaking, hopefully at this point you feel confident with all aspects of managing state in React, including updating objects in array state as well as lifting state up. React, in its purest form, is a library for building user interfaces. It's so simple that the entire mental model can be represented as a formula where your view is simply a function of your state. Though this equation gives us a simple mental model for how React works, there's one aspect of the equation that still, after all these years, seems to confuse people. Exactly when and how is f invoked? Or said differently, exactly when and how does React update the view? To better answer this, instead of starting with how or when, let's go back one step further.
What? Check this out, right?
What is rendering? Put simply, rendering is just a fancy way of saying that React calls your component with the intent of eventually updating the view. When React renders a component, two things happen. First, React creates a snapshot of your component, which captures everything React needs to update the view at that particular moment in time. Props, state, event handlers, and a description of the UI based on those props and state are all captured in the snapshot. From there, React takes that description of the UI and uses it to update the view. To get the starting UI of your application, React will do an initial render starting at the root of your app. To create a root, you first get the HTML element you want to mount your React app to, pass that to React.dom's createRoot function, then call root.render, passing it a React element which React will use as the starting point to get the initial UI of your application. Unless you're building a React app from scratch, this is usually done for you by whatever generates your app. Of course, this initial render is the most uninteresting one. Without the ability to re-render, React would be mostly useless. This naturally leads us to our next question. When exactly does React re-render a component? Looking back to our equation, your intuition might be that f is invoked whenever s changes. That would make sense. We wouldn't want to recalculate the view unless the state had changed. In fact, it's as simple as that. React will only re-render when the state of a component changes. With that, we now have our final interrogative. How? How does React actually know when the state of a component has changed? At this point, it's fairly trivial and, once again, it has to do with our snapshot. When an event handler is invoked, that event handler has access to the props and state as they were in the moment in time when the snapshot was created. From there, if the event handler contains an invocation of useState's updater function, and React sees that the new state is different than the state in the snapshot, React will trigger a re-render of the component, creating a new snapshot and updating the view. So now at this point, you have a high-level theoretical mental model for how React renders and then re-renders whenever state changes. But like any mental model, it's only helpful in as much as it can withstand the stress test of reality. Let's do that now. Let's say we wanted a simple app that allowed a user to click a button and toggle different greetings. To do this, we'll stick all of our greetings in an array, and then we'll have a piece of state that keeps track of the index of the greeting we want to display. We'll then have a button that when it's clicked will either increment the index or reset it back to 0 if we've reached the end of the array. Now, whenever our button is clicked, our handleClick event handler will run. The state index inside of handleClick will be the same as the state in the most recent snapshot. From there, React sees there's a call to set index, and the value that was passed to it is different than the state in the snapshot, triggering a re-render. Let's take a look at another example. In this code, when the button is clicked, what gets alerted? Don't trick yourself into thinking that all of a sudden things are now somehow different and more complex than they were prior to you seeing this example. We know that when our handleClick event handler runs, it has access to the props and state as they were in the moment in time when the snapshot was created. In that moment, status was clean. Therefore, when we alert status, we get clean. Now, if we click the button again, you'll notice that because our previous button click triggered a re-render and created a new snapshot with the status of dirty, on any clicks after the initial click, we get dirty. Let's try another one. What happens when we click the button in this example? When the button is clicked, React runs our event handler and sees that we invoke an updater function inside of it. From there, it calculates the new state to be 0. It then notices the new state, 0, is the same as the state in the snapshot. Therefore, React does not trigger a re-render and the snapshot and view remain the same. Again, React will only re-render if the event handler contains an invocation of useState's updater function and React sees that the new state is different than the state in the snapshot. How about this one? What will count be after the button is clicked? Again, we know that when our handle-click event handler runs, it has access to the props and state as they were in the moment in time when the snapshot was created. In that moment, count was 0. So eventually, once React is done calculating the new state, it'll see that the new state, 1, is different than the state in the snapshot. From there, React will re-render the component, creating a new snapshot and updating the view. Once you understand how rendering works, these kinds of questions become trivial to walk through. But there is one question that may have come up looking at this example. How many times will the counter component re-render when the button is clicked? Your intuition might be that React will re-render for every update or function it encounters, so 3 times in our example. Thankfully, that's not right since it would lead to a lot of unnecessary re-renders. Instead, React will only re-render after it's taken into account every update or function inside of the event handler and it's sure what the final state is. So in our example, React will only re-render once per click. Now you may have noticed something. React only re-rendering once it's taken into account every update or function inside of the event handler implies that React has some sort of internal algorithm it uses to calculate the new state. React refers to this algorithm as batching. Thankfully, it's pretty straightforward. Whenever React encounters multiple invocations of the same updater function, it will keep track of each of them, but only the result of the last invocation will be used as the new state. So in this example, the new state will of course be 3. Now it's uncommon, but there is a way to tell React to use the value of the previous invocation's updater function instead of replacing it. To do that, you pass the updater function a function itself that will take in the value from the most recent invocation as its argument. In this example, C will be 2 since that's what was passed to the most recent invocation of setCount before our callback function ran. Therefore, the final state will be 2 plus 3 or 5. What about this one? The state will be 1, then it will be 1 plus 3 or 4, then it will be 7, then it will be 7 plus 10 or 17. Notice that we don't use 4 in the third invocation even though that's what's returned in the second invocation. That's because we're telling React to just forget everything it knew and use 7 as the new state. Another way to think about this code is like this, where React just ignores the previous value unless you explicitly use it. Are you having fun yet?
Zero fun, sir. All right.
Let's look at another example. After clicking our button 3 times, what will the UI show? What will be logged to the console, and how many times will app have re-rendered? This example not only validates our mental model because it clearly demonstrates the difference between the values that are captured when the snapshot is created, those that get logged, and the values as they are after the component re-renders, but it also shows us another interesting aspect of how React re-renders. That is, React will only re-render once per event handler, even if that event handler contains updates for multiple pieces of state. This is yet another example of how React will only re-render a component when it absolutely has to. With that in mind, let's look at another example that may surprise you. Let's start with our greeting code from earlier. Now let's say we wanted to make our greeting component a little more welcoming. To do that, we'll create and render a wave component inside of greeting that will add a wave emoji in the top right of the UI. Notice anything interesting about how our app works? Try to guess when our nested wave component will re-render. Your intuition is probably thinking, never. After all, if React truly only re-renders when it absolutely has to, why would Wave ever re-render since it doesn't accept any props and has no state? Let's add a log to Wave so we can see when it actually renders. Interesting. Notice that Wave re-renders whenever we click the button, changing the index state inside of greeting. This may not be intuitive, but it demonstrates an important aspect of React. Whenever state changes, React will re-render the component that owns the state and all of its child components, regardless of whether or not those child components accept any props. Now, I get this may seem like a strange default. Shouldn't React only re-render child components if their props change? Anything else seems like a waste. First, React is very good at rendering. If you have a performance problem, the reality is it's rarely because of too many renders. Second, the assumption that React should only re-render child components if their props change works in a world where React components are always pure and props are the only thing these components need to render. The problem is that isn't always the case. Third, if you do have an expensive component and you want the component to opt out of this default behavior and only re-render when its props change, you can use React's React.memo higher order component. React.memo is a function that takes in a React component as an argument and returns a new React component that will only re-render if its props change. Now, regardless of how many times we click our button, Wave will only render once on the initial render. But again, even when dealing with child components, our mental model holds strong. Anytime a component renders, regardless of why or where it's located in the component tree, React creates a snapshot of the component which captures everything React needs to update the view at that particular moment in time. Props, state, event handlers, and a description of the UI based on those props and state are all captured in the snapshot. From there, React takes that description of the UI and uses it to update the view. Now, before we end, there's one more thing we need to address. You may have heard of React's strict mode component. It's React's way of saying, what if we took this really simple mental model and just blew it up? That's an exaggeration, but it does change things just a little bit. Whenever you have strict mode enabled, React will re-render your component an extra time. All of our examples until this point have had strict mode disabled. This may seem strange, but strict mode makes sure your app is resilient to re-renders and that your components are pure. Regardless of if React renders once or 100 times, because your view should be a function of your state, it shouldn't matter. Strict mode helps you make sure that's the case. The way you enable strict mode is by wrapping it around your app like this. Similar to creating your root, unless you're building a React app from scratch, this is usually done for you by whatever generates your app. Now, one last question you probably have. Doesn't this have performance implications? Yes, but React will only respect strict mode when you're in development mode. In production, it'll be ignored. Up until this point, we've seen how beautifully simple React is in its purest form. You encapsulate UI, state, and event handlers into components, compose those components together, passing data down the component tree as needed via props. The problem, of course, is nothing muddies the simplicity of a mental model quite like the complexities of reality. In the real world, it's not uncommon to need to do things outside of React. Fetching data from a server, interacting directly with the DOM, or even using native browser APIs like setTimeout or local storage are all examples of real-world use cases that don't fit neatly into React's model. For React to be of any practical use and not just a theoretical tool we learn about in computer science programs,
one valid bit, one modified bit, one reference bit.
It needs to handle these outside world use cases and do so in a way that doesn't completely destroy the simplicity of the mental model. That's what this section is dedicated to, learning how to get React to play nicely with the outside world. In the previous lesson, we established 3 rules for managing effects in React. Now that you have some rules to guide you, let's stress test them a bit with some more advanced use cases. So at this point, all of our examples have been side effects that are local to the user's device, getting their battery level, accessing local storage, changing the document's title. But when you think of a side effect, especially as someone building for the web, the one that most likely comes to mind first is network requests. Without the ability to manage the complexity of asynchronous side effects like network requests, React would be mostly useless. Thankfully, we've already established a nice mental model for how we can do this. To demonstrate it, let's say we were building a carousel-like experience whose content was different Pokemon from the Poke API. Now, before we jump into the code, I want you, knowing what you already know now about how to handle side effects in React, to think through how you might implement this. We know based on rule number 0 that we need to keep our network requests out of React's rendering flow. Now we just need to decide where we put it, either in an event handler or in useEffect. Your first intuition is probably to put it in an event handler. Whenever the user interacts with our carousel, we'll make a network request to asynchronously fetch the next Pokemon. That seems perfectly reasonable. Unfortunately, it's the wrong approach. This becomes obvious when we break it down further. What exactly does whenever the user interacts with our carousel actually mean? When they click a button? What about navigating with our keyboard? What if we wanted our carousel to change Pokemon automatically every few seconds? What about on the initial render when there's no user interaction, but we still need to fetch the first Pokemon? The takeaway here is there's no single event that should trigger our network request. Instead, what we're really wanting is to synchronize our component with the result of calling the Poke API, the perfect use case for useEffect. Before we worry about the async bits, let's build out the basic logic for our carousel first. Again, the entire premise of this app is to synchronize our component with the result of calling the Poke API. To do that, we'll need some state. Specifically, we'll add an ID state to keep track of the ID of the Pokemon we're currently viewing, and a Pokemon state to keep track of the actual Pokemon data. Our ID state will default to 1, since that's the ID of the first Pokemon, Bulbasaur.
I choose you, Bulbasaur. Go! Bulbasaur.
We'll then encapsulate the async logic for fetching Pokemon into a function called fetchPokemon. Now, whenever we call fetchPokemon passing it an ID of the Pokemon we want to fetch, we'll get back an object with an error if there was one, or a response of the Pokemon data if there wasn't. Now, the fun part. Again, we want to synchronize our local Pokemon state with the Poke API according to our local ID state. That's just a fancy way of saying whenever our local ID state changes, we want to invoke fetch Pokemon, passing it the new ID. We'll do that by calling fetch Pokemon inside of useEffect and then updating our Pokemon state with the result. There are a few interesting things to point out with this code. First, notice that our dependency array only includes one element, ID. Again, this isn't telling React to rerun the effect when ID changes, though technically that's what's happening. Instead, we're giving React an array of all of the dependencies our effect needs to resynchronize with the outside system. As a byproduct of that, whenever React sees that ID has changed between renders, it will rerun the effect. Second, you may be wondering why we declared a new handle fetch Pokemon function inside of our effect. This is purely aesthetic and was done so that we could use async await inside of useEffect. Third, this is tutorial code. Currently, we're pretending like loading and error states don't exist. Unfortunately, you can't write tutorial code at work, so let's fix that. First, we'll need to add two new pieces of state to our component, loading and error. Because fetch Pokemon is invoked as a result of rendering, including the initial render, we'll initialize loading to true and error to null. Now we need our effect to manage our new loading and error states. Thankfully, our fetch Pokemon function makes this easy since it's so explicit if there's an error. What we'll do is whenever our effect runs, reset loading and error back to their default values before we make the network request. Then, once we get back a response, if there's an error, we'll update error, and if not, we'll update Pokemon before setting loading to false. Now, don't get freaked out over the multiple separate invocations of our updater function. Remember, React batches these together intelligently, so there's no wasted renders. So at this point, you could argue the hardest parts are behind us. It appears we've successfully abstracted the arduous async side effect bits into useEffect and are now synchronizing our component with the Poke API. At this point, all we need to do is update the UI to both show our active Pokemon and allow the user, or the app itself, to change it via our carousel. These components are extraneous to the point of this lesson, so I'll just put them in here so you can see them. Notice the simplicity of our app now. Because we've told useEffect to synchronize our local Pokemon state with the Poke API according to ID, we've taken what has historically been the most complex parts of building a web app, an asynchronous side effect, and made it an implementation detail behind simply updating ID via our handle previous and handle next functions. Now, unfortunately, we're not quite done yet. As is, our code contains the worst kind of bug, one that is both inconspicuous and deceptively wasteful. Can you spot it? If not, here's a hint. What happens if, before we get back a response from the Poke API, we change ID? Whenever we call fetch Pokemon, because it's an asynchronous request, we have no idea how long that request will take to resolve. It's completely possible that, while we're in the process of waiting for a response, our carousel updates ID, which causes a re-render, which causes our effect to run again with a different ID. In this scenario, we now have two requests in flight, both with different IDs. Worse, we have no way of knowing which one will resolve first. In both scenarios, we're calling set Pokemon when the request resolves. That means, because we don't know in which order they'll resolve, Pokemon, and therefore our UI, will eventually be whatever request was resolved last. To make it worse, you'll also get a flash of the Pokemon that resolved first before the second one does. This is a pretty subpar experience. How do we go about fixing it? Really what we want is to tell React to ignore any responses that come from requests that were made in effects that are no longer relevant. In order to do that, of course, we need a way to know if an effect is the latest one. If not, then we should ignore the response and not set Pokemon inside of it. Thankfully, React makes this pretty easy with the last remaining feature of useEffect you haven't seen yet, the cleanup function. If you return a function from your effect, React will call that function each time before it ever calls your effect again, and then one final time when the component is removed from the DOM. We can see this in action by adding a cleanup function to our effect that logs the ID that the effect is associated with. Notice that our cleanup function is only called for IDs that are no longer relevant. This makes sense because the cleanup function for the most recent effect won't be called until either another effect runs, making it stale, or the component has been removed from the DOM, which is irrelevant in this scenario. We can use this knowledge along with the power of JavaScript to fix our problem. Whenever the effect runs, let's make a variable called ignore and set it to false. Then whenever the cleanup function runs, which we know will only happen when the effect is stale, we'll set ignore to true. Then all we have to do before we call set Pokemon or set error is to check if ignore is true. If it is, then we'll just do nothing. Now, regardless of how many times ID changes, we'll ignore every response that isn't in the most recent effect. This not only makes our app more performant, but it also improves the UX since React will now only re-render with the latest Pokemon. Now I know you're having the time of your life, but this will be the last scenario we look at for now, and it's one you'll see often. Let's say we were writing software for a company that administers certifications for employees. To earn a certification, an employee must pass an online test by a certain percentage. Part of the test is that for every time the employee tabs away from the current window, they lose their percentage. How would we go about encapsulating this requirement into a React component, letting the student know how many times they've tabbed away? Here's a hint. We can use the document's visibility change event to detect when the page is no longer visible. First, let's add some state to track the number of times the employee has tabbed away. We'll call this count, and we'll also add some UI for the user to see their count. Now the tricky part. We need to listen for the visibility change event and update our count state accordingly. Since we're synchronizing the document's visibility status with our component, we'll use useEffect. First, let's add our event listener. Remember, whenever you add an event listener, you also need to remove it when the component is removed from the DOM, or you'll have a memory leak. useEffect's cleanup function makes this simple. Now all we need to do is update our handle change function to increment our count state whenever the document is no longer visible. Your first intuition might be to do something like this, where we add count to our dependency array and then increment it by 1 inside of handle change. Whenever the document's visibility state is no longer visible, we increment count by 1. Simple, right? Yes, but actually no. In fact, even though our app appears to be working fine, there's one major problem. Can you spot it? Via our dependency array, we've told React that our effect depends on our count state, which is true. That means whenever count changes, React will re-render and then, once it's done, re-invoke the effect. The problem is every time React calls our effect, we're removing the previous event listener and adding a new one. That's not ideal. We can see this in action if we add some logs to our effect and tab away and back to the page. We're in a weird spot. We only want React to add our event listener once on the initial mount, but we need to include count in the dependency array because we're using it inside of the effect to calculate the new count state. What's interesting about this example compared to our other examples is, even though we're using count in the effect, we're not using it as a way to synchronize our component with some external system. So we don't actually need React to rerun the effect when it changes. Thankfully, React has a solution for these types of scenarios, and it's probably not what you'd expect. In fact, it has nothing to do with useEffect at all. Instead, it has to do with how we're updating our count state. Right now, and in almost every other scenario where you're updating state, you pass the state's updater function the value with which you want to replace the current state. However, an often overlooked aspect of this API is you're also able to pass the state's updater function a function itself, and when React invokes that function, it'll pass it the current state. You can then use that to calculate the new state. In both of these examples, we're telling React to increment count by 1. However, the difference is in how we're getting access to the current state of count before we increment it. In the first example, we're relying on a closure, and therefore we have to specify count inside of the dependency array. In the second, we're not, since React will pass us the current state of count as an argument, and therefore we don't need to include it in the dependency array. With this knowledge, we can now update our example to remove count from the dependency array, which prevents React from rerunning our effect every time it changes. So now, hopefully at this point, you're starting to get a solid grasp of how you can use the rules we've been building throughout this lesson to better establish a mental model for managing side effects in React. Before you go, there are just a few smaller details I want to point out that didn't fit into the normal narrative flow of this lesson, but I think are important to know. First is how strict mode affects useEffect. If you're not familiar, strict mode is a component that comes with React that allows you to stress test your application in development. When you have strict mode enabled, which is the default for most React apps, React will re-render an extra time, rerun effects an extra time, and check for deprecated APIs. Why is this helpful? Well, you can think of strict mode as a stress test of our 3 rules. If render is not pure or you're incorrectly managing side effect, strict mode will aggressively uncover that. It's controversial, but the whole goal of strict mode is to make it more obvious that you're doing something wrong, which I think is a reasonable goal. If you stick to the rules we've established in this lesson, strict mode will mostly be irrelevant for you. Next are what React calls reactive values. Throughout this lesson, you may have been wondering the distinction between what needs to be included in useEffect's dependency array and what doesn't. For example, why doesn't local storage, number, or set index need to be included in our greeting effect? The reason is because they're not reactive values. Defined, a reactive value is any value that can change between renders. props, state, or any variable defined inside of a component are all reactive values, and therefore always need to be included in the dependency array if they're in the effect. In our example, local storage and number are always going to be referentially equal across renders, and React guarantees that the setIndexUpdater function will also always be consistent across renders, meaning all of these are non-reactive values. Again, this makes sense if you think about it. The whole goal of useEffect is to synchronize your component with some outside system. Non-reactive values are irrelevant to useEffect because they're never used in the synchronization process. Now, one final thing. The rules we've established will work for 95% of the use cases you'll encounter when dealing with side effects in React. As these last few lessons have already been long enough, we'll cover that other 5% in a later lesson. But if you're curious, here's the full list of rules I follow, including that 5%. I want to start this lesson off a little different than we usually do. That is, with a challenge. Given this code, the goal being to create a stopwatch component that allows the user to start and stop the timer, can you spot the bug in it? Here's a hint. What happens when we try to stop the timer? Go ahead and press pause if you need more time. The bug is in how we're storing the ID that is returned from our setInterval invocation. Right now, we're storing it as a normal JavaScript variable. What that means is that every time React re-renders, the value of ID will be reset to null. Then when the user stops the stopwatch, we're passing null to clear interval, which of course does nothing. To fix this, instead of recreating ID on every render, what we want to do is tell React to preserve ID across renders. Isn't this the exact use case that useState was created for? Let's try it. Now when the user stops the stopwatch, we're passing the correct ID to clear interval because it doesn't get reset when our component re-renders. So at this point, we're good, right? Not quite. Yes, our app technically does work, but throughout this course, you've been taught, nauseatingly, that in React, your view is simply a function of your state. As is, our app breaks this mental model. We've introduced state that has nothing to do with our view. We're simply using it as a way to preserve a value across renders. That's what we call hacky. What we need is a way to tell React that we want to preserve a value across renders, but that value has nothing to do with the view, and therefore React doesn't need to re-render when it changes. Luckily for us, React provides an escape hatch for this exact scenario called useRef. useRef creates a value that is preserved across renders, but it won't trigger a re-render when it changes. The API is fairly simple. When you call useRef, what you get back is a ref, which is an object with a mutable current property whose value will be preserved across renders. Like useState, you can specify the initial value of the ref's current property by passing an argument to useRef when you invoke it. Unlike useState, this current property is mutable, which is really just a fancy way of saying that you can change it directly, and doing so won't trigger a re-render. Now we can use our knowledge of useRef to update our stopwatch example from earlier. We'll swap out our ID state for a ref and use that to store the ID that setInterval returns. Much better. We no longer have any state that isn't used to update the view, and more importantly, we're potentially saving React some work since our app no longer re-renders when we store the ID. Let's look at another example. Say we had an animation where CSS is doing all the heavy lifting, and all we're doing with React is keeping track of the state of the toggle input, something like this. You'll notice that our app is mostly fine, but there's one thing I think we can improve on. If you click on the toggle switch repeatedly, over and over, the experience breaks down. Now it still works, but I think the better UX is to only allow the user to toggle when the animation has finished running. Because CSS is doing a lot of the heavy lifting, we don't have a ton of options for how to solve this. One approach that I think is good enough is to disable the toggle switch for a short period of time after it's been clicked, say 1300 milliseconds. To do this, let's preserve a timestamp of the last time the toggle button was clicked. Then, when it's clicked again, we'll only call setActive if more than 1300 milliseconds has passed. Since this value we want to preserve has nothing to do with rendering the UI, and we don't want React to re-render it when it changes, we'll store it in a ref. Now, because we're using a ref to preserve the last time the button was clicked, we can use that to disable our toggle button without getting in React's way. So at this point in the course, if we were to summarize the mental model of React that we've built up, it would look something like this. In React, your view is a function of your state, both of which you encapsulate inside of a component. To get your application, you compose all of your components together. To get data down the component tree, you use props. To get data up the component tree, you use callbacks. Sometimes you need to do things that don't fit into the regular React paradigm. These are called side effects, and React provides some escape hatches for these scenarios. If you have a side effect that is triggered by an event, put it in an event handler. If you have a side effect that is synchronizing your component with some outside system, put it inside of useEffect. If you need to preserve a value across renders, but the value has nothing to do with the view, and therefore React doesn't need to re-render when it changes, put it in a ref using useRef. So far, so good. There's just one more side effect that we haven't talked about yet, and it's crucial for building on the web: interacting directly with the DOM. Now I know it seems a little weird. Isn't the whole point of React to create an abstraction over the view, or the DOM, so you don't have to directly interact with it? Yes, mostly. But again, they're called escape hatches for a reason.
Hold on to your butts.
Take this scenario. Say we worked for a really hip marketing agency out of Soma. We're tasked with making one of those toolbars that you can click and scroll to different sections of the page. Knowing what you know about React, how would you go about solving this? If you have some experience with DOM APIs, you might be familiar with the scroll into view method. It's a method that you can call on any DOM element, and the browser will scroll the element into view, naturally. This would be perfect for us if we had access to the element we wanted to scroll to. One idea might be to just say, screw it. Use the DOM's getElementByClassNames method to manually grab the element we want to scroll to. This actually works, but it's brittle, unnecessarily dependent on string matching, and not very Reacty. In fact, it kind of feels like we're giving React the middle finger since we're bypassing it directly and going straight to the DOM. Instead of needing to query the DOM directly, React comes with an escape hatch that allows us to reference any DOM element that it creates, and it does so by utilizing what we learned about earlier, refs. Whenever you pass a ref as a prop to a React element, React will put a reference to the DOM node it creates into the ref's current property. Of course, manually manipulating the DOM like this is a bad idea, since that's React's job and React will have no insight into the changes you make, but it does make for a good representation for how DOM refs work. So now that we know how to use refs to get access to DOM nodes, let's update our scrolling example from earlier. We'll create 3 refs, one for each of our sections. We'll then attach those to their own DOM element and call scroll into view on them when they're clicked. Much better. Now we have complete control over which elements we scroll to, and we're no longer dependent on class names or the layout of the DOM. Again, this works because when you pass a ref as a prop to a React element, React will put a reference to the DOM node it creates into the ref's current property. Now there's one thing that's been eating me up since earlier. It's when I was talking about our toggle switch, and I said that one approach I thought was good enough was to disable the toggle switch for a short period of time after it's been clicked, 1300 milliseconds. Now this worked, but it too was also brittle. If a designer tweaked how long our animation took to run, it wouldn't behave as expected. At the time, all we knew about useRef was that it allowed us to preserve a value across renders without triggering a re-render when it changed. What we didn't know was how we could use it to get access to DOM nodes, and specifically in our example, determine when all of the CSS animations had finished for a particular DOM node. So let's do some refactoring. Now, before we go on, I do want to say that I would consider everything after this to be advanced. Don't get down on yourself if it's a little confusing at first. I've been writing React since 2014, and it even took me a little while to get a solution I was happy with. With that said, it's a fantastic example of everything we've learned up until this point in the course to properly utilize escape hatches in React. We'll start by getting the easy parts out of the way. Let's get rid of our old code by keeping track of the last time the toggle button was clicked and create 2 new refs. One to get access to the root div element, so we can use the browser's getAnimations method on it, and the other to keep track of if the CSS animations are still running, so we can avoid calling setActive if they are. Now the hard part, figuring out if we have any CSS animations running and keeping our animating ref up to date with that information. In a way, what we're really trying to do is synchronize the current state of our CSS animations with our component. This, by definition, is the perfect use case for useEffect. To do this, inside of our effect, we'll use the browser's getAnimations API to get all of the animations in our entire subtree. Next, we'll map over all of our animations, creating an array of promises that will each resolve once its animation has finished running. Then, once we have our array of promises, we can use promise.all to wait for all of them to resolve, which they will once all of the animations have finished. Finally, the whole point of this, we want to update our animating ref both at the beginning and the end of this process to keep it in sync with the current state of our animations. Now, instead of disabling our toggle switch for an arbitrary amount of time, we only disable it for the exact amount of time it takes for all of our animations to finish running. So to recap, we learned about useRef, a hook that allows you to create a value that is preserved across renders, but won't trigger a re-render when it changes. We also learned that if you pass a ref as a prop to a React element, React will put a reference to the DOM node it creates into that ref's current property. Whenever you have an app that is a collection of components, there's a linear relationship between the size of your application and how difficult it is to share state across that application. What you've been taught is that whenever you have state that multiple components depend on, you'll want to lift that state up to the nearest parent component and then pass it down via props. This works most of the time. But what happens if instead of your app looking like this, it looked like this? It's rare, but there are times when passing props through intermediate components can become overly redundant at best or completely unmanageable at worst. Take a library like React Router. Even if you've never used React Router before, it's probably not surprising to you that in order to work, it needs the ability to pass routing data to any component in the component tree, regardless of how deeply nested the components are. Or React International, a library for handling internationalization and localization that needs to be able to pass locale data to any component in the component tree, again, regardless of how deeply nested the components are. Because this is such an obvious limitation of a component-based architecture, React comes with a built-in API to solve it called context. You can think of context as giving you the ability to teleport data anywhere in your component tree without needing to pass props. That's literally all it does. It's the wormhole, TARDIS, Stargate, Portkey, DeLorean of React. Now the question becomes, how do we use it? Well, if you think about it, there are really just a few things you need to know for a feature like this. First, creating the context. Second, deciding what to teleport and where. And third, getting the teleported data from inside the component.
Jesus Christ, Doc, you disintegrated Einstein.
Let's start with creating the context. This one is pretty simple. You can create a context by calling react.createContext. Next is deciding what we want to teleport and to which part of our app we want to make it available. What's nice about context is it gives you granular control over which parts of your component tree have access to the data that you're teleporting. Here's how it works. When you create a new context, what React gives you is an object with a provider property. Provider accepts a value prop, which is the data that you want to teleport to any component in the provider subtree. Now, because we've wrapped our entire app in provider, any component, regardless of how nested it is, can get access to what we passed to value. And finally, to get access to what was passed to the provider's value prop, you can use React's useContext hook, passing it the context as the first argument. Notice that even though our cafe's 80 component is a few layers deep and doesn't receive any props, we can still access the Marty object via useContext. In a way, you can think of using context as creating shadow props, where you're making data available to a component just without having to explicitly pass it down. Now, admittedly, there is one thing strange about this demo you may have noticed. Since Marty is just a static object, why don't we just export it from a module and import it wherever we need it? There's not really a need for context in this scenario. The reason I chose this example is because it demonstrates how context works without having to worry about managing state. And in fact, as we saw, it has nothing to do with state at all. Context is purely just a mechanism for teleporting data. This is a huge misconception when it comes to context. Whether what you're teleporting is a static object, function, state, or anything else, it doesn't change the fact that context is a teleporter, not a manager of state. This also makes context a little difficult to teach. It's not that context itself is difficult, as you saw, it's that context is most appropriately used in large applications with deeply nested component architectures where passing props becomes unreasonable. So, by definition, it's hard to create a small demo app that represents that use case. With that said, let's move our example a little closer to reality by teleporting state instead of just a static object. More specifically, let's move Marty into an array, add his friend Doc, and then teleport that array of passengers. Note that after updating what we're teleporting to be an array, we also need to update where we're consuming the data, in this case, the Cafe 80s component. But other than that, notice nothing else changed. One more time for those in the back, context isn't a way to manage state. It's a way to teleport data. The management of our state, in this case, is done by useState, not context. Now, one question you may be wondering, how does React handle re-rendering when the data you're teleporting changes? The answer is satisfyingly simple. React re-renders the same way it always does, when state changes. In our example, passengers is located at the root of our application. Therefore, whenever it changes, React will re-render the entire tree, passing the new passengers as the value of context. Now, before we wrap up, there's just one small thing to know about how context works, and it has to do with setting a default value for the context. Whenever you invoke useContext, passing it a context object, it'll return whatever you pass to the value prop of the nearest provider component of the same context. However, what if there is no parent provider? In this case, it'll get the value from the first argument that was passed to create context when the context object was created. Now, if we invoke useContext passing in our DeLorean context, without previously rendering a parent DeLorean provider component, the return value will be our array. Here's a clever use case of this. Can you tell what's going on here? We take advantage of the fact that if there is no parent provider component, useContext will get the value from the first argument that was passed to create context when the context object was created. This allows us to have more granular control over reading the value from context. It can either be what was passed as a value prop to the provider component, or what was passed as the first argument when the context was created. Now, just one final thing before we finish.
These guys are hammers, and to hammers everything looks like nails.
I heard that.
Typically when you first learn about context, it appears like it's the solution to a lot of your problems. Just remember, there's nothing wrong with passing props down multiple levels. That's literally how React was designed. I don't have a universal rule for when you should and shouldn't use context, just be mindful that it is common to overuse it. The Green Bay Packers, fresh off a devastating loss in the Super Bowl the previous season, had convened for the first day of training camp in July of 1961. The players were eager to get to work, anxiously awaiting the necessary adjustments needed to bring home a championship. But their coach, the legendary Vince Lombardi, had other plans. He began the team meeting with a simple and now fabled statement. Gentlemen, this is a football. Every season, regardless of the team's prior success, would start in the same way, with a deep emphasis on the fundamentals.
A successful play is not just the result of the partnership of 2 or 3 men. It is the result of the coordination of all 11 men, each of whom has made himself master of all the fundamentals on which winning football is founded. Every man must be committed to excellence. Every man must be committed to victory.
I want to start this lesson off in a similar manner by looking at what I would consider to be the most fundamental array method in JavaScript, the for-each method. The whole purpose of for-each is it allows you to invoke a provided function for each element in an array. Say we had an array of numbers instead of strings. Using for-each, how would we add all of the numbers together to get a single value? Odds are you'd probably do something like this. Notice that in order to add up all the values, we needed to add another value, state, and mutate it on each iteration. This works, but it's not ideal for a few different reasons. First, it's dependent on the state of our application. Second, it's modifying state outside of its own scope. By definition, this makes for each an impure function. While not always bad, it's best to avoid impure functions when you can. To accomplish the same functionality with a pure function, we can use what's called the reducer pattern. The reducer pattern is a functional programming pattern that takes a collection as input and returns a single value as output. In JavaScript, the most common use of the reducer pattern is the reduce method that all arrays have access to. If we refactored our example from earlier to utilize reduce, our input would be our numbers array, and our output would be the summation of every value in that array. The key difference between reduce and for each is that reduce is able to keep track of the accumulated state internally without relying upon or modifying state outside of its own scope. That's what makes it pure. The way it does this is, for each element in the collection, it invokes a reducer function passing it 2 arguments, the accumulated state and the current element in the collection. What the reducer function returns will be passed as the first argument to the next invocation of the reducer until there are no more elements left, when it'll return the final value. So here's what we know so far. The reducer pattern is a functional programming pattern that takes a collection as input and returns a single value as output. The way you get to that single value is by invoking a reducer function for every element in the collection. Now, instead of using this pattern to transform a collection into a value, how can we use it to accomplish the main goal of this course, creating a better, more resilient user interface? Let's reframe it a bit. What if instead of our collection being an array, it was a collection of user actions that happened over time? Then, whenever a new user action occurred, we could invoke our reducer function to get the new state of our application. Check this out. Don't worry about the details yet, just know that we're using the exact same reducer function, but instead of invoking it manually, we're invoking it when a user clicks the button. It might seem strange, but since this is just a pattern, there's no reason we can't utilize it to create a more predictable interface. Now the question is, how? Because it's such a helpful pattern, React comes with a built-in hook called useReducer that accomplishes the same thing as useState, but allows you to manage your state using the reducer pattern. The API for useReducer is similar to what we saw earlier with array.reduce, but with one big difference. Instead of just returning the state, similar to useState, useReducer also returns a way to update that state. What's different is instead of returning an updater function, it returns a function called dispatch that when called, will invoke the reducer function. Putting it all together, here's what it looks like. Again, notice our reducer is still the exact same. The only difference is that instead of the reducer getting the value from an array, it's getting it from whatever was passed to dispatch. In our example, 1. Said differently, when invoked, whatever you pass to dispatch will be passed as the second argument to the reducer function. which we've been calling value. The first argument, which we've been calling state, will be passed implicitly by React, and it represents the current state of the reducer. Again, everything is the exact same as what we saw earlier with JavaScript's reduce method, but now it's a user event that triggers the reducer function. So at this point, you've seen how useReducer works in its most basic form. What you haven't seen yet is an example of useReducer that resembles anything close to what you see in the real world. To get closer to that, let's add a little bit of functionality to our app. Instead of just incrementing count, let's add 2 more buttons, one to decrement and one to reset it to 0. For decrementing, all we need to do is pass -1 to dispatch, because math. For resetting the count to 0, it gets a little trickier. Right now, with how we've set up our reducer function, there's no way to specify different types of actions that can occur to update our state. We only accept a value, which we get from whatever was passed to dispatch, and add that to the state. What if instead of dispatching the value directly, we dispatch the type of action that occurred? That way, based on the action type, our reducer can decide how to update the state. With the current functionality of our app, we'll have 3 different action types: increment, decrement, and reset. Now, inside of our reducer, we can change how we update the state based on those action types. Instead of naming our second parameter value, let's change it to action to better represent what it is. This is where we start to see useReducer shine. You may not have noticed it, but we've completely decoupled the logic for managing count from the component itself by mapping actions directly to state transitions inside of our reducer. This means all the component has to do is dispatch what action occurred, and how the state changes in response to that action is an implementation detail of our reducer function. Now, before we continue, if the lesson has felt slow so far, this is the moment where it's going to start picking up. And if this lesson hasn't felt slow, that's fine. Just make sure you're comfortable with everything we've covered so far before moving on. Now let's change our app just a little bit. Instead of just incrementing and decrementing count by 1, let's let the user decide via a slider. To accomplish this, imagine we had a slider component that took in 3 props: min, max, and onChange. The way we get the value of the slider is via the slider's onChange prop. Knowing this, and knowing that it's the value of the slider that will decide by how much we increment and decrement count, what changes do we need to make to our app? Right now, the state of our reducer is an integer which represents the count. This worked previously, but now instead of just managing count, we also want our reducer to manage another piece of state, step, which we get from our slider. Instead of state just being an integer, let's refactor it to be an object. This way, any new values that our reducer needs to manage, like our new step value coming from the slider, can go as properties on our object. Now, since our state is no longer an integer but an object with count and step properties, we'll need to update our reducer to account for that. Notice that we always return an object with the same shape, and now we're accessing count as a property on that state object. Also notice that in all of our cases so far, increment, decrement, and reset, we're just passing along the current value of step. This makes sense. We don't want to change step when any of these actions occur. So now that our reducer is updated to work with the new shape of our state, the next thing we need to do is update state whenever the user moves the slider. If you'll remember, we get access to that slider value by passing an onChange function to our slider component. Whenever the user moves the slider, the onChange function will be called with the new value of the slider, giving us the opportunity to update the step property on our state. But now we have another issue. What do we dispatch? Up until this point, we've been able to dispatch the type of action that occurred: increment, decrement, or reset. This worked fine, but we're running into its limitations. Along with the type of action that occurred, we now also need to pass along some other data. Specifically in our case, we want to pass along the value of this slider so we can use that to update our step state. You might be tempted to do something like this, where you pass any extra data as a second argument to dispatch. Unfortunately, this won't work because the dispatch function only accepts a single argument. To work around this, what if instead of dispatching a string, we dispatched an object? Then, like we saw earlier, we could pass along any extra data as properties on that object. Here's what our existing event handlers would look like if we did that. Notice that each object we dispatch has a type property to represent the type of action that occurred. And here's a new event handler we could pass to our slider's onChange prop. In this one, notice that we're passing along the step value as a property on the action object. Now that we've updated what we're dispatching to be an object instead of a string, there are 3 changes we need to make to our reducer. First, we need to refactor all of our conditional statements to check for the type property on the action object. Second, we need to add another conditional for our new action type, update step. Notice that we're using action.step in order to update the step property on our state. This was the whole reason we needed to refactor action to be an object instead of an array, so that we could pass that step property along in the object. And finally, we need to update increment and decrement to adjust count based on the step property instead of just one. With that, we see another subtle but powerful benefit of useReducer you might have missed. Because the reducer function is passed the current state as the first argument, it's simple to update one piece of state based on another piece of state. In our example, we can see this in how we're updating count based on the value of step. In fact, I'd go as far as to say whenever updating one piece of state depends on the value of another piece of state, reach for useReducer. So at this point, we've seen how useReducer works and some of the advantages it gives us. Now let's dive a little bit deeper into those advantages and answer the question I know you've been thinking. When should you use useReducer instead of useState? Fundamentally, useState and useReducer accomplish the same thing. They both allow you to add state to a component that will be preserved across renders and will trigger a re-render when it changes. There are, however, a few situations when you'd want to use one over the other. Here's one example. Imagine we were creating a component that was responsible for allowing a user to register for our newsletter. This form needs to collect 3 pieces of information from the user: their name, email, and if they agree to our terms of service. For UX purposes, we'll also need 2 more pieces of state: submitting and error. Using useState, here's one approach for how we'd accomplish this. First, there's nothing technically wrong with this code. It works just fine. However, it is an imperative solution to the problem. We're operationally describing how we want to submit the user's email with lots of set invocations. Instead, what if we took a more declarative approach? Instead of how, let's describe what we're trying to accomplish. We can do this by leveraging useReducer. The reason useReducer can be more declarative is because it allows us to map actions to state transitions. This means instead of having a collection of set invocations, we can simply dispatch the action that occurred. Then our reducer can encapsulate the imperative instructional-like code. Notice that we're describing what we want to do: submit. Then, based on the result, success, or error. That's a lot cleaner and easier to reason about than our imperative solution. The rest of this code isn't particularly interesting or covering anything new, but we'll quickly walk through it for completeness. First, we'll build out our reducer, updating our state based on those 3 actions. Then we'll update our form component to useReducer instead of useState. If you ever find yourself needing a more declarative approach to updating your component state, give useReducer a shot. Now, before we end, let's take a look at one more use case where useReducer works better than useState. To make it fun, I want to offer it as a challenge. Here's our counter implementation we saw earlier, but implemented with useState instead of useReducer. What I want you to do is, using useEffect and setInterval, increment the counter by step every second. So count will change both whenever the user clicks a button or every second. Pause the video, scroll down to the section in the post, and give it a shot. All right, let me guess the steps you went through. First, you probably started with something like this. That's clean and aggressively wrong. Remember, handle increment uses count and step, which means you need to declare them in your dependency array. The problem, of course, is if you include them in your dependency array, your app will blow up because you'll be clearing and establishing a new interval every time count or step changes. Not ideal. From there, you probably remember that if you pass a function to an updater function, you'll get access to the current state without needing to pass it into the dependency array. That probably led you to try something like this. Nice. That seems like it works, but can you spot the problem with it? Try changing step. It's the same problem we ran into before. Every time step changes, we're clearing and establishing a new interval. Better, but still not ideal. Believe it or not, useReducer can help us with this situation. Again, with useReducer, we decouple how the state is updated from the action that triggered the update. This means that we can trigger a state change from inside of our effect without needing to worry about including any of the current state properties as dependencies to useEffect. Now our effect is only called once, regardless of how many times counter or step change. So to recap, like useState, useReducer allows you to add state to a component that will be preserved across renders and trigger a re-render when it changes. Unlike useState, useReducer allows you to manage that state using the reducer pattern. useReducer also offers a bit more flexibility than useState since it allows you to decouple how the state is updated from the action that triggered the update, typically leading to more declarative state updates. If different pieces of state update independently from one another, useState should work fine. If your state tends to be updated together, or if updating one piece of state is based on another piece of state, go with useReducer. It may seem strange, but one of the most fundamental steps on the road to mastering React is getting comfortable with the concept of referential equality in JavaScript. Now, I know, if I was on a game show and had to come up with the most overcomplicated sentence I could, it'd probably contain the words referential equality in JavaScript. But I promise it's not as bad as it sounds. To help us understand it, and therefore help us take one of the final steps in mastering React, we first have to take a step back and talk about what is arguably the most fundamental aspect of JavaScript itself: value types. Whenever you create a variable in JavaScript, that variable can store one of 2 types of data: a primitive value, or a reference value. If the value is a number, string, boolean, undefined, null, or symbol, it's a primitive value. If it's anything else, it's a reference value. On the surface, primitive values and reference values look the same, but under the hood they behave much differently. The key difference can be seen in how they store their value in memory. If you looked at the in-memory value of a primitive, you'd see the actual value itself. If you looked at the in-memory value of a reference type, you'd see a reference to a spot in memory. That's cool, but in practice, what difference does it make? Let's take a look at some examples. Though a little strange, this example demonstrates an important aspect of primitive values, that the in-memory value of a primitive is the value itself. Therefore, when we assign one primitive to another, like we're doing with display name, what we're really doing is copying the value from one spot in memory to another. So even though last name changes and display name uses last name, display name itself doesn't change because it copied the value of last name when it was created. Now let's look at a similar example, but instead of using a primitive value, let's use a reference value. Notice the difference. When we create a new variable and assign it to a reference value, like we're doing with Snoop, what we're really doing is copying the reference to the spot in memory where the value is stored. Then, because both values point to the same spot in memory, when we modify the value at the location in memory, it'll affect both values that reference it, Snoop and Leo. Now there's one more interesting difference between primitive and reference values, and that's how the identity operator compares them. Here we can see that because name and friend have the same value, Tyler, when comparing them, we get true. This probably seems obvious, but it's important to realize that the reason we get true is because with the identity operator, primitives are compared by their value. Since both values equal Tyler, comparing them evaluates to true. Now, what about reference values? Even though Leo and Laito have the same properties and values, when comparing them with the identity operator, we get false. The reason for that is because, unlike primitive values which are compared by their value, reference values are compared by their location in memory. Unless two reference values have the same location in memory, the identity operator will say they're false, and therefore not referentially equal. Now, before we get to why this knowledge is fundamental to mastering React, let's stress test your understanding a little bit. What does this evaluate to? This one is true, since both A and B point to the same spot in memory. When comparing reference values, again, the identity operator compares the memory address of the value, not the value itself. What about this one? This one evaluates to false since both objects are stored in different spots in memory. When comparing reference values, the identity operator compares the memory address of the value, not the value itself. This one? This evaluates to false since functions are reference values and both functions are stored in different spots in memory. This one? This one evaluates to true since both C and D point to the same spot in memory. This one. This evaluates to false. Notice we're invoking the functions, which gives us back an empty object. Again, when comparing reference values, the identity operator compares the memory address of the value, not the value itself. And here's the last one. This one evaluates to false since both arrays are stored in different spots in memory. Now the question you've been waiting for. What does referential equality have to do with React? Let's answer that with an example. If you remember, the way React works is that whenever state changes, it will re-render the component that owns that state and all of its child components, regardless of whether or not those child components accept any props. If you have an expensive component, and you want that component to opt out of this default behavior by only re-rendering when its props change, you can use React's React.memo higher order component. You may remember this example, which wraps our wave component inside of React.memo so that it only re-renders when its props change, which as of right now is never since it has no props. Now, regardless of how many times we click our button, wave will only render once on the initial render. Now let's make our wave component a little bit more configurable. Instead of receiving no props, let's pass it an options prop that we can use to configure the emoji. Specifically, we'll allow the consumer of Wave to be able to configure the emoji skin tone as well as if it's animated. Now, if we refactor our Wave component to utilize these props, we're left with something like this. That works great, but can you spot the problem now? Notice what happens when we change the greeting. Even though we're using React.memo, our Wave component is back to re-rendering every time index changes, even though it doesn't rely on index at all. Can you spot why that is? Here's a clue. It has to do with referential equality. The way React.memo works is it'll only re-render the component when its props change. But that brings up an interesting question. How exactly does React determine if the props have changed? Simple, with the identity operator. Okay, technically it uses object.is to check if the props have changed, but for all intents and purposes, you can think of them as being the same. Their only difference is in their treatment of signed zeros and NaN values. You're going to be awesome at the next JavaScript bar trivia night. Now the way our wave component works is we're passing in object, which is a reference value, as a prop. As we saw earlier, because reference values are compared by their location in memory, even though the properties on our object never change, we're technically recreating and passing a brand new object on every render, nullifying the benefits of React.memo. So how do we fix this? Well, we need to figure out a way for the object we pass as a prop to be referentially consistent across renders. One simple solution would be to just move our object outside of the component. That way, it will be created once when the module is loaded, but not recreated on every render. That works, as now our wave component doesn't re-render when index changes, but it only works in this particular scenario where the properties and values on our object are static and don't depend on the context of our component. What would happen if we wanted to make the tone property dynamic? Let's say we want to give the user the ability to update tone by clicking on the wave emoji. To do that, we'd have to move our object back into our component, something like this, and then refactor our wave component to accept the new onClick prop. Now this works, but again, we're nullifying the benefits of React.memo since we're now recreating a new object on every render. Not only that, but we're also recreating the handle wave click function on every render as well. What we really want to do is figure out a way to memoize both our options object and our handle click function so that their references only change when tone does. That way, when React.memo uses object.is to compare props, it'll work as we want. Thankfully, React comes with a built-in hook that does exactly this called useMemo. Defined, useMemo lets you cache the result of a calculation between renders. The first argument is a function that returns the value you want to cache, and the second argument is, similar to useEffect, an array of dependencies that the function depends on. If any of the dependencies change, the cached value will be recalculated. To memoize our options object, we can do something like this. Now, unless wave index changes, the options object will be referentially identical across renders. We can do something similar for our handle wave click function as well, except instead of caching an object, we'll cache a function. We can even refactor this a bit to not have that wave index dependency. Instead of relying on the wave index state via closures, we can pass setWaveIndex a function and get access to it there. Now, if we throw both of these in our app, notice that when we change our greeting, Wave no longer re-renders since both of its props are referentially the same as the previous render. Now, there is one more refactor we can make to our code, but it's purely syntactic. Whenever you need to memoize a function, instead of returning a function from useMemo as we're currently doing, you can use React's useCallback hook to make it a little easier. It works exactly the same as useMemo, except instead of caching the result of calling a function, it caches the function itself. If we refactor our handle wave click function, it'll now look like this. Notice that useCallback is really just a simple abstraction over useMemo. In my opinion, it probably shouldn't exist since you can just use useMemo, but it does, so you might as well use it. Now, if we add our handle wave click function to our app, you'll notice it behaves the same as before. You'll often hear about useMemo and useCallback as ways to increase the performance of a React app by skipping unnecessary re-renders. And though that's mostly true, in practice, I found that it's much more common to use them as ways to create referentially consistent values, and specifically, referentially consistent values across renders. This is a natural byproduct of so many hooks utilizing a dependency array to determine what values have changed between renders. To truly master React, which is the ultimate goal of this course, you need the understanding to recognize different approaches for solving the same problem and the knowledge to choose the optimal solution. There's no problem you'll find in this lesson that you don't already have the tools to solve. However, like using a butter knife to cut a steak, some tools are better or worse than others in specific situations. If you take a peek into the dark crevices of the React API, you'll find two of these specialized tools, both designed to solve advanced use cases around managing effects in React. Now, I get it. Yes, we've already had a few lessons on managing side effects in React, and yes, those were the longest in the course. Mastery is fun, effects are hard. Let's keep going. If you remember back to that lesson, we established a list of rules we could follow for effectively managing side effects in React. Now, before you get too overwhelmed, know that these 3 rules cover 95% of use cases you'll see when dealing with side effects in React. Unfortunately, that 5% still exists, and it stands in the way of your mastery. Per usual, let's start with an example. Say we were building a basic app that showed the browser's current dimensions, as well as a mini browser that mirrored those dimensions. The solution to this is pretty basic. We're synchronizing the browser's dimensions with our component, so we'll use useEffect, which updates some local state. If you were to implement this yourself, my guess is it would look something like this. This works, but there's a slight problem. Without knowing exactly what the problem is, you may have missed it. Let me slow it down for you. For a microsecond, until our effect runs and updates the state, the browser dimensions are null. This means that on the initial render of our app, anywhere where we use size.width or size.height won't render properly. Even worse, once our effect runs and updates our state, our app will fix itself, causing an aggressive flicker of our UI. The primary reason this happens is because useEffect runs asynchronously after render. This is almost always what we want, as it optimizes for showing the UI to the user as quickly as possible. However, in this scenario, we actually want our effect to run synchronously before React shows anything to the user. Now, this makes sense if you think about it. Our UI is dependent on the browser's dimensions. We don't want to show the user anything until we're sure what those dimensions are. This is the exact use case that React's useLayoutEffect hook was designed for. React guarantees that the code inside useLayoutEffect and any state updates scheduled inside it will be processed before the browser repaints the screen. This lets your component use layout information for rendering, as we're doing in our example with the browser's dimensions. The API for useLayoutEffect is identical to useEffect, so to make it work, all we have to do is swap out useEffect for useLayoutEffect. Our artificial delay is still in place, but notice now, React doesn't show anything to the user until after it's run useLayoutEffect and updated our state. This way, the first time the user sees anything, it will be with the layout information. The way I like to think about it is if I have a side effect that is synchronizing layout information with my component, use useLayoutEffect instead of useEffect to make sure that the first time a user sees anything, it'll be with the layout information. And with that, we have our next rule. If a side effect is synchronizing your component with some outside system, and that side effect needs to run before the browser paints the screen, put that side effect inside of useLayoutEffect. The only thing to keep in mind with useLayoutEffect is you don't want to use it unnecessarily. If you're not synchronizing layout information with your component, you don't need it. Unless you absolutely have to, turns out intentionally blocking React from updating the UI is not a great idea. Now let's look at another scenario. Say we were building an app that worked both online and off. As part of the UI, we want to display the current status of the user's network connection. If I were to ask you to build this, odds are you take a similar approach that we did earlier, useEffect with some useState. Now this works and there's nothing wrong with it, but there is some duplication going on here. Essentially all we're trying to do is subscribe to the browser's internal navigator.online state. However, in order to do that, we're creating and then managing another piece of state, network status, inside of our component. That seems redundant. If the browser is already keeping track of the user's network state via navigator.online, why do we need our own network status state? The answer to that is simple. So React knows when to re-render and update the UI. That's, of course, how React works. Components only re-render when their state changes. Surely there's not an exception to the rule because that would invalidate our entire mental model of how React works, right? Unfortunately, there is. But thankfully, our model is still intact. In scenarios where a piece of non-React state is already being managed by some outside system, whether that's the browser, another library, or even your own custom data store, you can use React's built-in useSyncExternalStore hook to subscribe a component to that state without needing to redundantly duplicate it as React state inside of your component. The reason it doesn't break our mental model is because our view is still a function of our state. However, in this one scenario, our state lives and is being managed by something outside of React. So how exactly does useSyncExternalStore work? Well, if you think about it, there are really just two things a hook like this would need. First, a way to read the external state, which we'll call getSnapshot. And second, a way to subscribe to the external store so it knows when it changes. We'll call this subscribe. Let's start with getSnapshot. As mentioned, all it needs to do is return the current value of the external store. In our case, that's navigator.online. Next is subscribe. This is where we're going to listen to the browser's online and offline events like we previously did in useEffect. However, instead of creating our own function, which we called handleChange, that updates some local piece of React state, subscribe takes in a callback function that we can pass as the event handler. Now, whenever the online or offline events occur, the callback function will be invoked, which will tell React to invoke getSnapshot in order to re-render the component with the latest value of navigator.online. Now there's no need to manage a redundant piece of state, and we can be sure that if we see a component using useSyncExternalStore, that component is subscribed to a piece of state that lives and is managed outside of React. With that, we have our fifth and final rule for managing side effects in React. If a side effect is subscribing to an external store, use the useSyncExternalStore hook. Now, as always, There are a few things to be aware of when using useSyncExternalStore, and per usual with React, they all have to do with referential equality. You'll notice that in our example, both subscribe and getSnapshot live outside of our component. This is convenient because it allows us to decouple our subscription logic from our component, but there's also another more practical benefit to this as well. The way useSyncExternalStore determines that it should re-render the component or that it should resubscribe to the store is via referential equality. If the subscribe function changes between renders, then useSyncExternalStore will resubscribe to the store. Similarly, if the value returned from getSnapshot changes between renders, then React will trigger a re-render of the component because it thinks the state has changed. We can see this in action by moving subscribe into the component. Now notice what happens when we change the greeting. Every time network indicator re-renders, because we've defined subscribe inside of the component, React thinks it's a new function and will unsubscribe, then resubscribe to that store. That's obviously not ideal. The solution is to either move subscribe outside of the component as we did earlier so it never changes, or if you need to keep it inside of the component, you can use useCallback so its reference is stable. Now, since subscribe's reference is stable, React will only subscribe once on the initial render. Similarly, if the value you return from getSnapshot is a reference value like an object or an array, and that reference value isn't memoized, then you'll throw React into an infinite loop scenario since useSyncExternalStore will re-render every time a reference value changes, which would be every render. We'll see an example of how to get around this later in the course, but the quick version is to always return a primitive value from getSnapshot, or if you can't, memoize the reference value so you only return a new object when it has actually changed. And with that, we have our final 5 rules for managing side effects in React. Because don't repeat yourself is a principle of software development and not one of education, let's recap everything we know about React's useEffect hook one last time. The whole purpose of useEffect is to encapsulate a side effect that synchronizes your component with some outside system. It works by removing the side effect from React's rendering flow and delaying its execution until it's safe to do so, after the component has rendered. useEffect will invoke its effect once after the initial render of the component, and then again after every render in which a value in its dependency array has changed since the previous render. In almost every scenario, this is what you want. You're synchronizing your component with some outside system, and as such, you want to resynchronize whenever a dependency changes. However, what do we do in a scenario like this? All we're wanting to do is pass along some state information for our analytics. However, because state is a reactive value, we need to include it in the dependency array. This gets React off our back, but now we have another problem. Anytime state changes, our effect will rerun and mess up our analytics. What we really need in this moment is a way to tell React that we want to use a reactive value inside of useEffect, but that reactive value has nothing to do with synchronizing the component and therefore shouldn't need to be included in the dependency array. This is kind of what React's useEffect event hook allows us to do. However, instead of using it to tell React which reactive but non-synchronizing values we want to use inside of useEffect, we can use it as a way to abstract those values into their own event handlers, which we can then use inside of useEffect without needing to include it in the dependency array. Similar to how event handlers allow us to abstract our side effect logic out of React's rendering flow, useEffect event allows us to abstract our reactive but non-synchronizing values out of useEffect. The biggest thing to notice is that URL is still included in the dependency array and we're passing it as an argument to onPageView. This is good practice as it makes it explicit which values are synchronizing, URL, and which aren't, state. So now that you've got the basic idea, let's look at a real example. Say you were building a counter app that counted up from 0, but allowed the user to specify the duration between increments, something like this. To accomplish this, we'll have 2 pieces of state, count and delay. Then inside of useEffect, we'll have a use interval to increment count every delay milliseconds. Simple enough. Every time delay changes, React will remove the previous interval and create a new one. Now, how could we go about implementing something like this, where the user can decide by how much we increment count? First, we'll add another piece of state for the step, an event handler to update that state, and a slider hook up to the event handler. Now, instead of incrementing count by 1 every delay milliseconds, we want to increment count by step every delay milliseconds. That seems easy enough, but it does put us in a weird spot with our useEffect's dependency array. We either leave it out and have React yell at us, or worse, we include it and unnecessarily remove and re-add our interval whenever delay or step changes. This is a similar problem to what we saw earlier. We need to access the reactive step value from inside of useEffect, but we don't want to include it in the dependency array because it has nothing to do with setting and removing our interval. This is the perfect use case for useEffect event. All we have to do is abstract our reactive but non-synchronizing logic into useEffect event, then we can use that event handler inside of useEffect without needing to include it as a dependency. So to recap, whenever you need to access a reactive but non-synchronizing value inside of useEffect, look into abstracting that logic into useEffect event. And if it's still a little fuzzy, we'll see plenty of use cases for this in the next section. Now, before you go, you may remember back to a previous lesson where we used useReducer to solve a similar problem. Because useReducer allows us to decouple how the state is updated from the action that triggered that update, it allows us to trigger a state change from inside of an effect without needing to worry about including current state properties in the dependency array. This works, and it's still valid, but sometimes it's nice to not have to refactor your code to use a different pattern. Let's take a step back and do a quick review on what we know about React so far, which admittedly is quite a bit. React is a library for building user interfaces. With React, your view is a function of your application state. All you have to do is worry about how the state in your application changes, and React will handle the rest. The primary mode of encapsulation for this concept is the component, which encapsulates both the visual representation of our particular piece of UI, as well as the state and logic that goes along with it. By doing so, the same intuition you have about creating and composing together functions can directly apply to creating and composing components. However, instead of composing functions together to get some value, you compose components together to get some UI. To accomplish this, React needed a way to allow you to describe what the UI for a component would look like from inside the component itself. This thinking led to the creation of JSX, a wonderful love child of HTML and JavaScript that allows you to write HTML-ish looking syntax directly inside of JavaScript. What made JSX different was it combined the power and expressiveness of JavaScript with the readability and accessibility of HTML. At this point, components were a beautiful solution for encapsulating and composing UI. In fact, when you think about composition in React, odds are you think in terms of UI composition. This is natural since it's what React is so good at. The problem is in the real world, there's more to building an app than just the UI layer. It's not common to need to compose and reuse non-visual logic as well. However, because React couples UI to a component, historically this was difficult. This is the problem that hooks were created to solve. Just like a component enabled the composition and reusability of UI, hooks enabled the composition and reusability of non-visual logic. Here's every hook we know so far. With all of these hooks, and with all we've covered so far, there's still one more aspect of React that I would consider fundamental and necessary knowledge. Per usual, let's discover it with an example. If you remember back to the advanced effects lesson, we had an app that displayed the user's current network status. We implemented it like this, using React's useSyncExternalStore hook. Now here's a question I want you to think through. Let's say we wanted to display the user's network status in another part of our app. How would we go about doing that? Because we've coupled the logic for determining the user's network status to the component that displays it, if we wanted to reuse that logic, we'd be forced to copy and paste it into another component. Isn't the whole purpose of hooks, as mentioned earlier, to enable the composition and reusability of non-visual logic? If that's the case, copying and pasting non-visual logic all over our app doesn't seem like the most elegant solution. What if, just like React comes with its own set of hooks, we were also able to make our own custom hooks? In that scenario, a custom useNetworkStatus hook would be awfully convenient. As you probably guessed by now, not only is this possible, but it's highly encouraged whenever you want to reuse non-visual logic. Here's what that custom useNetworkStatus hook would look like. Notice it's just a function that starts with use, and it uses another hook, useSyncExternalStore, inside of it. That is literally the definition of a custom hook. Now, anywhere inside of our app where we need the user's network status, we can use our useNetworkStatus hook. Now, one question you may have is why exactly does a hook need to start with use? That seems overly restrictive. The reason is so it's clear where the Reacty features of the component are, whether that's state, effects, or any other hooks. If you see a function call that starts with use, you can be sure that it's utilizing other hooks inside of it. The second part of the definition is also important. If the function doesn't call other hooks, whether those hooks are built-in React hooks or other custom hooks, then it's not a hook. It's just a function and doesn't need to start with use. Now, the only question left is, when is it appropriate to create custom hooks? The answer, per usual with React, is to rely on your intuition. The same intuition you've developed about functions and when to create them can be directly applied to creating hooks. Mostly, you'll know it when you see it. If that's too abstract, the next section will give you a few, 50 to be exact, ideas for when to create them. Now is the time where you are going to take everything you've learned in the course so far, and you are going to use it in order to build out use hooks which is a library that we built for the course, which is a collection of modern server-safe React hooks. It is a real library. You can go ahead and install it. It's got a GitHub, it's got issues, it's got everything you'd expect from a real production-ready hooks library. So what you can expect is this is going to look a lot like the challenges interface you're used to. Notice here we go from use document title all the way down to use long pressed. This is in order of difficulty. So these ones up here, pretty simple. As you get to about right here, they start to get a little bit more difficult, all the way down to use long press, which if you feel comfortable with everything we've discussed in the course so far, you'll be able to knock it out, but it is the most difficult hook in the course, in my opinion. With that said, let's take a look at what these look like. So what you're given is this challenge interface here. It gives you a description of the hook. In this case, use local storage gives you a convenient interface for storing and retrieving data from local storage. Its API is similar to useState, but it stores the value it returns inside of local state. So you get a description, you get how the hook is used. In this case, it takes in a key as well as an initial value. It returns you an array, just like useState, with state and a way to update that state. It gives you a bunch of tasks to follow. And of course, it gives you the final result down here, where if we add some stuff here and then we refresh this, notice that it gets persisted because it is in local storage. So what I would do if I were you, read the description, understand how it's used, and then I would actually come to the official documentation, make sure you understand the parameters it takes in, the return value. You can scroll down here for how it's used in an actual application again, and then I would start implementing it yourself. As always, if you do get stuck, you can check out the Solutions tab. That has the video of me walking through building the hook, as well as a bunch of hints that you can use. And then, of course, at the very bottom, you get the finished code. Now, before you start, I would make sure that you are comfortable with everything we've talked about up until this point in the course. What's cool about use hooks, but also the difficult part, is that it does use every aspect of what we covered in the course so far. Use state, use effect, obviously, use layout effect, using external store, use effective end. Everything we've talked about in the course is going to show up in at least one hook. So make sure you are comfortable with all of that. And another cool thing about use hooks is a lot of these are going to be wrappers over DOM APIs. So for example, use copy to clipboard, use preferred language, use lock body scroll, use window size, use event listener, use intersection observer. All of these under the hood are using browser APIs. So not only will this make you better at React, it will also make you a better web developer. And don't be afraid, for example, like some of these, where's use media query? Right here, this one is really just using the Match Media API under the hood. So don't be afraid to jump into MDN to see how a lot of these work, because in order to implement the hook, obviously you'll need to know about Match Media. And again, that's what the tips in the Solutions tab is for. It'll walk you through all of the APIs that you need to know that are browser-specific APIs. Again, this is going to be challenging, it's going to be difficult, but by the time you get through it, not only will you know pretty much everything there is to know about React, but you'll also learn a lot about browser APIs along the way. So with that, again, if you get stuck, always create a new thread in the discussion and we will be there to help you out. Good luck.